or models category. So method will be broadly, there are several types of method, OLS, ML kind of thing. Broadly, I'll be focusing on the OLS part, and something, a line or two may be told with respect to maximum likelihood method. Then the method with respect to classical linear regression model, and some supplementary base required that whenever we'll be progressing with the advanced versions of execution of regression, then we need to know certain type of technical points, or some terminologies need to be well explained before. So like something called variance or the standard deviation, or there is something called standard error, whether they are same, or there is any existence of any difference between them. Then how do you go for hypothesis testing? There may be several types of testing of hypothesis. Broadly, I'll be focusing on the T test and F test because they will be broadly used in our regression analysis. Then there will be a component of goodness of fit, basically R square or adjusted R square, and some other versions of it available. So as you progress further, under the base category, supplementary base category, I will be discussing that. Then going to the third phase of course, in the course, I will demonstrate with the help of MS Excel how to execute a simple regression, and how to execute multiple regression. By the way, what is the meaning of them, and how do you progress with it with respect to data visualization or discrete statistics, then correlation, or then determination process, and how do you interpret whatever the results come out with the help of any software. Right now we are focusing on MS Excel. So whatever results come out, how do you interpret that? Then subsequently, the diagnosis part will be broadly categorized into four categories on the basis of certain assumptions which is required for GLRM. And when they are violated, they come out with certain problems, and those problems, how far they are affecting the what you call the robustness or the parsimony nature of our regression result. Then on that basis, we'll be diagnose them. And diagnosis may give rise to certain type of problems or errors, and accordingly we'll be discussing them one after another. So covering multicollinearity, autocorrelation, heteroscedasticity, and something called model specification. These are the four important parts that I'm going to cover now. So start with the what you call the anatomy or the philosophy or the framework behind regression analysis. So before going to do any kind of bivariate analysis, because regression is basically a relationship between two variables. So depending on the nature of data, whether we are referring to a cross-sectional data or time series data, or whether there is a pooled cross-section with time series, which is known as panel data, on that basis, as you can see, that I have demonstrated something with respect to over here by saying that something like dependent variable or any variable, y is not necessarily the dependent variable over here. It can be any variable, whether dependent or independent. Gradually, we'll come to know that what is the meaning of dependent or independent. But any variable, when it is collected with respect to a given time period, but the observations will be for different states, or maybe different blocks within a district, or maybe different districts within a state, or maybe different countries across the globe. Then those type of arrangement will be a cross-sectional arrangement, and generally we write with respect to a subscript called I, where I represent that there are different types of cross-sectional element, and time period is fixed. For any given period of time, we are doing this type of analysis. Now, reverse to this, if you go to the second part of the story, so here I is replaced by some subscript called T, where objective is to focus on any one aspect of cross-sectional element. Like, for example, a country is the cross-sectional element. And suppose for a country level, we need something called GDP or money supply or any other variable, then accordingly, those variable can be represented in terms of YT, XT, ZT kind of thing, where T varies from 1 to N or T, depending on how many time period we are interested to analyze. And on that basis, the arrangement of data will give rise to time series data. And subsequently, there is something called pooled data, pooled cross-sectional data, or broadly panel data. So there exists a little bit difference between panel and pooled data. But broadly, if you want to understand that combination of cross-sectional along with time series, then it will give rise to something called a panel data harassment. So on the basis of these three types of data, the three types of econometrics arises, and accordingly cross-sectional econometrics or time series econometrics or panel data econometrics, they are the broad things. And because of the nature of today's presentation is a simpler one, so I'm not going to the panel data analysis for the time being. But anyway, the today's lecture will be a balanced combination of cross-sectional and time series data, or cross-sectional econometrics and time series econometrics. So, coming to the second part of the philosophy or the anatomy of this model, so there is a component of linearity. So, whenever we come across with regression model, even if it is told to us or not told to us, the implicit version of regression is linear. But anyway, subsequently, when we come to the end of our today's session, then the non-linearity component also be subject matter of our discussion. So in that case, the linearity, when you say linearity of a regression model, so as you can see from the equation which is mentioned over here, this yi represents over here, y is the left hand side variable before the equation, before the equality sign over here. And in the right hand side, as we can see, there are several what you call uh, letters are there, and those several letters, out of that, these i's, this x2, x3, xk, they represent the different types of right hand side variable. And broadly, the left hand side variable of a equation will be considered as a dependent variable, and the right hand side variable, they are considered as the independent variable. Again, a point of caution is that this rule is not universal in nature, because in the advanced version of econometrics, when there is a element of simultaneity or what you called endogeneity bias or something like that, so in that case, whichever is considered to be independent variable, they may come out with a dependent variable in some other cases. But to start with a very simple analysis, right hand side variable will be considered as the independent variable, and the left hand side is the dependent variable. Objective is that the independent variable, they affect the dependent variable, or in other words, y depends on the nature of x2, x3, up to xk. If there are varieties of what you call causes, which are determinants which are affecting the dependent variable, then those variables, they are considered as explanatory variable or predictor, sometimes known as covariates or regression. And the left hand side variable is known as the regression or simply dependent variable. The first point of introduction of econometrics is with respect to the additional term which is demonstrated over here in terms of U. Sometimes it is represented in terms of E in textbook, sometimes epsilon by some other type of terminology also. But broadly, they categorize something called a error term. The error term, which is broadly a random variable, or in other words, a stochastic term. We'll be gradually discussing what is the meaning of stochasticity, what is the meaning of randomness. So as we go to the next slide onwards, then those points will be getting clear. So if you want to write in terms of something called in a I mean sorted shorthand form, then those expressions with respect to a long part, they can be shortly represented in terms of yi is equal to b times x plus ey, where if you want to arrange it in terms of some vector or matrix notation, they have a different style of writing it. But I'm not going into details of that. That means the beta will be a vector of what you call parameters. Basically, the b1, b2 over here, the values are not changing. Only the thing is that the x2, x3, xk, even if the dependent variable, they are variable in nature because the values are not assumed to be constant. Now, those constant terms, that b1, b2, b3, they have a another version of it. We call it as a parameter, because the parameter and constant, they are different in the nature that b1 value is not known to us. When you say B1 is replaced by a number called 4 or 3 or maybe 2.5 or minus 7.8, any number, then accordingly, though that particular number will be considered as a constant term. So by the way, biations, the B1, B2, they are not changing in nature. So they are non-variable. And those non-variable, when they are general versions, we call it as a parameter. And when they are giving rise to a specific version of it, like some number, some specific number, we call it as a constant. And because we are not writing in terms of some numbers over here, so that's why those components will be considered as parameters. And broadly, the regression in econometrics, they are parametric exercises, although there are certain other versions of econometrics where the non-parametric exercises are also conducted. But anyway, as we have been restricting ourselves to very elementary level, so those non-parametric regression analysis are also beyond the scope for today's discussion. So this is the way in which we can analyze the first part of the story. So broadly, this deterministic component, which is, which we can determine, that will be, or that will be subject to what you call the change, either by the market mechanism or any mechanism which is revolving around us. And there is something called non-systematic or random component, because something cannot be modeled, everything cannot be modeled in a very simple manner, called by telling that the dependent and independent variable kind of arrangement. So some of them, those who are not covered over here, or maybe some what you call model specification thing, or maybe some measurement issues, anything whatever is left out which is not modeled by us, uh, then accordingly those non observable component, they will be considered or categorized under the error term category, or simply random or stochastic term category. So moving ahead with something more details about U. So this U is basically covering something called, this is a catch-all term basically, and this catch-all term, they are covering something called which is not available because of the data are not sufficiently available either for all the cross sections or maybe for all the time series. There may be certain type of measurement error, like something is in terms of rupees, some other variables they are measured in terms of kilogram or maybe liter or something like that. So in that way, the measurement units, when they're different to each other, they may give rise to certain type of error, and that is covered under the error term category, which is not modeled by us, but that is the outcome of our model. And then the last one is the intrinsic randomness in human behavior, because ultimately, whenever the whatever may be the source of data, whether it is primary or secondary, there is an element of human error. There is a possibility of element of human error, and that's why we may come across with some type of randomness in our modeling, and that's why those random component, they are covered under the U category. So basically, the U or the error term is the average effect of all the regression in the which is regression effect will be marginal, and whatever is not covered by all the regression, they will be captured under the catch-all term called the error term or the U. Now, coming to the concept of the parameter or the nature of the regression coefficient, those regression coefficients, they can be fixed in number, as we have seen previously. That's why we are not considering as parameter or uh, non-variable category in the sense. And there is also a branch of I do called econometrics, where that is called the Bayesian statistics or the Bayesian econometrics, where they treat the regression coefficients as random. So that advanced level is not covered over here. So what we are saying is that these regression coefficients, they are assumed to be parameters or not variable in nature. They are non-random in nature. So accordingly, that is another version of regression. And on that basis, the third component arises, that when whatever we say with respect to a linearity of the argument, so linearity does not necessarily mean the variables are linear in nature. The variables may have any type of nonlinear component, but the coefficients must be linear in nature. And whenever we are saying the coefficients, that means this B2, B3, or any beta 1 alpha terms are there, they should not be something like power of other than 1, or maybe a ratio of one parameter with another, like B1 by B2, or any logarithmic transformation of those things, because as we know, any type of transformation will be definitely giving us an impression that it will be non-linear in nature, whether it is exponential logarithmic transformation, or any type of base transformation, logarithmic base of a 10, or anything like that. So what we are trying to say is that linearity is always associated with the parameters. The parameter of any regression analysis should be linear in nature, but that is not restricted with respect to the variable. The dependent or the independent variable, they may be reciprocal in nature, like something divided by one divided by something, or maybe the ratio of two variable can be considered, or maybe something called a quadratic form, or a polynomial of order 2, or any n number, or anything logarithmic transformation is also feasible. So these are the three most important aspects of linear regression. And now moving into the what you call the philosophical base of, I mean, the base of this particular regression analysis. Um, the most what you called the prominent version of linear model is that there is a concept of classical linear regression model, or simply known as CLRM. And those CLRM, this is nothing but they have different what you call assumptions, and those assumptions, they play a very important role. And on because of which those assumptions, we consider the model to be the most what you call uh, uh, in other words, the one of the best version of any modeling, because it is based on certain very stringent assumptions, and those assumptions are if they found to be true in real situation, then that will be the most utopian state of affairs. Otherwise, it will not be a case. Otherwise, it will not be a case of what you call that will not be a subject matter of problem over here. Hello, any question?
No, no, continue, continue.
Okay. So to proceed with the regression model, is that the first thing is that it is linear in nature. So linearity indicates that they will be linear in parameters, and non-linear in, not necessarily linear to be in terms of variable in nature. I mean, parameters should be linear, not necessarily with respect to the right hand side or the left hand side variable. Second assumption is with respect to the stochasticity or the fixity nature of the regression, which we have also covered previously. The third variable is that given the value of any particular independent variable, the expected or the mean value of the error term is zero. That means what? How do you interpret it? That if there is an actual observation of your dependent variable, and if you fit a model on the basis of your regression analysis, then that will give rise to a predicted version of the dependent variable also. So ultimately, there is a chance available to cross-check how parsimonious your result is with respect to the actual observation of y. So if you have two series with you, y, which is real component, and predicted value of y or y hat, then if you find out its gap, then that will give rise to a series of error term. The third variable indicates that if you find out its mean value, that means because the error term sometimes will be plus and minus in the nature, that means predicted value may be little bit higher to the actual dependent variable. Sometimes it will be lying below it, or maybe lower to the actual value. So in that way, there will always be a positive and negative deviation arises. And if you go for a mean value of it, sum total of it, then accordingly what you can find that they will give rise to a zero value. If you are not getting your error term to be zero, ideally speaking, they will come out with zero. So, but if you come across with any such other observations, then accordingly that will be a problem, or that will be not in accordance with the CLRM principles or properties. So the fourth one is with respect to the variance of the error term. Those variance of the error term, given the values of the independent variable, they are assumed to be constant. That means the mean value will be zero, and the variance term, that means the dispersion measure, because one will be the central tendency measure of the error term. The second point or the fourth point over here is with respect to the degree of dispersion or measure of dispersion of the error term. They are assumed to be homoscedastic in nature. Homo means equal and scedastic means variance. That means the variance will be a constant term. If they vary along with the independent variable, then they give rise to a particular problem that is lead to the heteroscedasticity problem. So broadly, the assumption of the CLRM, they ruled out with any such of heteroscedasticity. Rather, they are saying that mean will be zero and the variance will be constant. Going to the fifth version of it indicates that the error terms should not be interrelated with each other. In other words, that means if you have the series of error term, which is basically the deviation between the actual y and the predicted y or the estimated y will be generated from our own way of regression and regression mechanism. Then those error term, if you arrange them as it is and a what do you call a lag behind it as it is, then that particular thing, that means one error term will be et, another error term will be a series of et minus 1. So the condition is that the previous values of error term should not be interrelated with the current values of the error term. That means if in 2019 there will be error term, then that error term should not be interrelated with its previous value. So accordingly, the previous value of the error term, it should not be interrelated with its further previous value and so on. So those correlation is known as autocorrelation, because error term, they may be supposed to interrelated with each other. So property is saying that there should not be any kind of such relationship allowed or correlation between two error terms. Obviously, two error terms means they are referring to one time period and the previous time period. So t minus 1 or t minus 1 with t minus 2, those type of error terms, there should not be any kind of correlation. That means last year observation of error term should not affect the current year's observations of error term. The current year observation of error term should be independent of the or they should not be in a position to affect the next year's error term and so on. So that otherwise hello. Okay. So moving further, the next version of it is that as you progress, in case of simple regression, there will be one independent variable, which will be most simple case. But in that case, the property 7 will not be, that will be value addition. That will not create any value addition. But in case of multiple right-hand side variable, when the x variables are many, maybe 2, 3, 4, basically large number of independent variable. So there is a possibility that any one independent variable may be interrelated with any other variable, or maybe multiple variables they are interrelated with each other. For example, the variable which is mentioned over here, the x2 variable is basically what you call, technically speaking, a linear combination of x3 and x4, where the x3 and x4 coefficients are 2 and 1 respectively. So accordingly, what happened, x2 variable is somehow interrelated with the variable of x3 and x4. So in that way, x2, x3, and x4, they are interrelated. So in that way, there is a possibility of multicollinearity problem. That means they may affect with each other. Anyway, in the further subsequent diagnosis problem, we will be discussing them in detail. So from the very beginning, so far as the base is concerned, the CLRM avoids the multicollinearity issue. That means there should not be any kind of such relationship. All the independent variables should be independent to each other. They should not affect each other, or there should not be any functional relationship between any independent variable with any other. So that is the another property of CLRM. Again, the same problem arises that if how far it is realistic or non-realistic, they are subject matter of our discussion when we go to the diagnosis part, to the end of our discussion. And coming to the specification thing, this is another important problem with respect to the CLRM. The CLRM says that there should not be any specification bias. Specification bias means if two variables are what you call linearly related, then the variable should be linear in nature. If there is an element of non-linearity, then we should be in a position to understand what is the nature of non-linearity, whether there is a existence of any quadratic equation, whether there is a possibility of any interaction term, whether there is a situation called logarithmic transformation will be feasible, and all such things should be properly spelled out, or it should be taken care of by the what you call the regressor, I mean the investigator. He or she should be in a position to address those issues properly. If there is any kind of specification problem arises, then accordingly the CLRM property will be violated, and accordingly whatever may be the nature of the outcome, there is a possibility of biasness or maybe inconsistency or maybe something called there will be further several other types of econometric issues may arise. So that's why the property says that there should not be any kind of specification bias. Whatever specification, which one is the best one, that should be properly spelled out. So final one, the error term follows a normal distribution. So that means normal distribution means, as you know that it will be a bell-shaped curve. So if you have the error terms with you, then the number of depending on the nature of regression, whether we have 30 observation, 20 observation, whatever, if you plot it in a graph paper, then it should be give rise to something a bell-shaped curve, where the measures of central tendency will be centered around to the peakness of that particular curve. It will divide the entire arrangement into two equal part, or broadly two equal part, 50-50%, or maybe nearly 50-50%. And accordingly, technically speaking, they should be giving rise to a mean value 0, and the standard deviation, or sorry, and the variance will be positive constant. So technically, these are the CLRM properties. If you have understood it, fine. If you have not understood it, basically from other social science point of view, there will be no such problem. Only two, three things need to be understood is that the arrangement should be proper one. There should not be any kind of problem like multicollinearity, autocorrelation, heteroscedasticity, or any model specification problem. That's why I have kept a large chunk of my discussion for those parts. So even if you miss this arrangement in terms of its philosophy, or maybe in terms of its what you call the technical specification, then it is not a problem. If you have not covered the 100% of it, we'll be discussing them with the help of some example, and then we'll be discussing them that this is the problem that we have highlighted a couple of minutes before, and if such problem arises, then this is the way in which we can detect it. If it is found to be detected, then some kind of what you call the solution need to be provided. So in that way, those matters can be easily taken care of. Maybe after 15-20 minutes, or after half an hour, we will be in a position to cover them in detail. Now, coming to the second part of the base indicates that there are different methods of solving the problem. So method will be, one of them will be the method of ordinary least square. So method of ordinary least square mechanism is that we have to find out the error term first. That means the dependent variable will be like previously, yi is equal to b1 plus b2 x2i, the arrangement in which we have demonstrated earlier. This initial arrangement, this equation 1 over here, this equation 1, if you keep ui in the left hand side and everything will be in the right hand side, then the arrangement will be something like this, as you can see over here. And thus error term, this equation 1, which is rewritten like this, if you go for a square term of it, that means if you go for the square term of the left hand side variable as well as the right hand side variable, and then sum it up, then those dependent variable, this is becomes what you call the square term of your error term. The square term of error term, if you minimize with respect to certain condition, then accordingly it will give rise to the efficient estimation, or the proper way of estimation of beta 1, b1, b2, b3, etc. What is the modality of doing that? For that, we need little bit of mathematics and advanced versions of derivation. So that's why I'm not going into the detailed part of executing OLS properly. That means how to derive OLS mechanism, and how the B1, B2, they are actually, what is the optimal way of calculating the B1, B2 and the other parameters. So technically speaking, this left hand side variable, we call it as the error sum of square or something called ESS. And similarly, some other components are also there. Gradually, we'll be discussing them. So now moving to other portions of properties of OLS. So the other properties of the OLS is that the final version of the OLS estimator will be something called blue. It will give you the best solution. If you are not well acquainted, I mean, if you are not getting it properly, if I can give you a analogical comparison with respect to microeconomics market structure, then as we know that perfect computation is considered to be the most what you call efficient market structure, right? Because it has a large number of what you call stringent assumptions, in the sense that commodities are homogeneous. There is I mean, the commodities are so closely substitute to each other that that means that the buyers will be indifferent between any seller one or seller two or something like that. So those type of things will be hardly feasible in the real market situation. And in the similar way, what you call the perfect competitive market structure, similar mechanism is also the case with respect to OLS estimator. That means a particular estimator is found to be the best one. It will be also something called linear in nature. There will be something called unbiased component of it, and those things will give rise to something called efficient. That means the linear component indicates that they are linear functions of the dependent variables. So obviously linearity means with respect to parameter, not with respect to the variables, as we have seen previously. The second part, that the estimators like B1, B2, B3, etc., they will be unbiased in nature. Unbiased means there will not be any repeated application of the method. On average, the estimator's approach to their true value. That means if you have some sample of 30 or 50 or 40 observations, and if you want to generalize with respect to 1 lakh people, or maybe very high large number of things, then what happen, whatever will be your characteristics of the sample estimate, they will be very true representative of the population analysis. And on that basis, the concept of unbiasedness will come. That means 30 people's analysis can give you that much clarity, or that much what you call scientific in nature, that it will give you the similar type of interpretation for very large number of populations. That is the concept of unbiased over here. The third point with respect to the class of linear unbiased estimator is that they should have a very minimum variance. Variance minimum because variance will be an indicator of dispersion. So even if it will be unbiased, but along with it, the straightness of that arrangement will be very large. So then accordingly, the straightness of any arrangement will not be, I mean, considered to be good. The arrangement should be in such a nature that the straightness of that arrangement should be as small as possible, and that straightness will be captured through considered as variance, and that leads to something called, it should give rise to very less variance, or they should have very minimum variance, and that minimum variance will give rise to efficient estimator. If the variance is found to be high, then accordingly that estimator will not consider to be inefficient one. So efficiency is one indicator, less variance efficient, high variance inefficient. On an average, sample observation will be close to the population. If they found to be same, then it will be unbiased. If the sample characteristics will be giving rise to a picture which is no way related to the population characteristics, rather they will be very far away cases will be found, then in that case we consider to be a biased answer, biased estimator. And biased estimator and what you call inefficient estimator, they should not be considered as a good estimator or best estimator. And that's why when you club them together, the linearity component along with unbiased, along with least variance, then they will give rise to something called best linear unbiased estimator, which is the property called blue property. And that is the beauty of this OLS estimator. And that is also a challenging part for the OLS estimator, because always blue may not be the case in the real situation. And if not, then what may be the problem, or what may be the outcome, that will be discussed subsequently. Then the some other type of base, which we call the supporting base for our further analysis, we need to understand that those estimators which we have discussed right now, those estimators, what is the concept of variance and standard error component over here? So as you have seen that previously there is a concept of ESS. That means if you find out the error term, now it is replaced by E. So don't be confused with U and E, because sometimes we use it as error term E, or maybe sometimes it is U written, but unless until they are defined otherwise, consider them as the same error term. So if you have the series of error term and square it up and get a sum total of it, then that will give rise to something called residual sum of square. And that residual sum of square, when it is deflated by the degrees of freedom is important, because whenever we are going for some sample, and sample size is represented by something called n, and k represents how many parameters are there. If you have two variable, one is dependent, another is independent, the parameters will be two. If you have multiple independent variable, then accordingly the parameters will be more. So accordingly, the degrees of freedom, it's depending on the values of n as well as k. High is n, that means larger is the sample size. Accordingly, degrees of freedom problem will be, I mean, degrees of freedom will be high. And accordingly, if the number of parameters will be more, then it will consume a lot of degrees of problem. That means suppose you have 30 observations, and if you have suppose 4 independent variable, then accordingly 4 plus 1 will be 5 parameters will be there. So 30 minus 5 will be 25, will be divided over here. Whereas if your number of observations will be 100, even if you go for the same 4 variable, then accordingly the k will be 5 now, and accordingly 100 minus 5 will be 95. So the jumping from 25 to 95, it simply depends on the number of sample size. So if your number of sample size will be very high, then accordingly degrees of freedom will be very high. Then when the degrees of freedom will be very high, then accordingly the variance term or the standard error term will be relatively less, because the error term will be standard error term is considered to be reciprocally, I mean inversely related with the degrees of freedom. Even if RSS is high, still then if your degrees of freedom is further high, then or very high, then in that case the ratio will give rise to a smaller variance, and accordingly standard error will be less. So accordingly, if your objective is to increase the standard error, not increase, rather standard error should be as small as possible, because variance should be as small, or the dispersion or the degree of spreadness should be as less as possible, so that we can make it as an efficient estimator. So on that basis, your sample size should be sufficiently large. And if the model allows you for a number of right hand side variable, then also it is okay. So ultimately, the final point of analysis, a final point of discussion over here is that whatever may be the nature of RSS, if you want to make your analysis to be a robust one, then in that case your sample size should be sufficiently very large. So in that case, it will capture all the problems, and it can solve many things to be many problems can be easily sorted out. So that's why if you're going for primary analysis or secondary analysis, whether your time series econometrics or cross sectional econometrics, always remember that if you have 30 or more than 30 observation, anyway there is no such rule of thumb, but anyway statistics, there is a concept of large sample small sample bias. So if you have a number 30 or more than 30, then majorly the degrees of freedom problem and the standard error component can be easily sorted out. Lower is standard error, better would be the result. So that's why this particular thing needs to be understood right now, and it depends on the number of sample and the number of in parameters. A number of parameters depend on how many independent variables you are taking into your discussion or into your analysis. Now, coming to the next part of our discussion with respect to hypothesis testing. So, hypothesis testing indicates that there can be two types of broadly testing. In other words, there can be n number of hypothesis testing processes are available, but we are focusing right now two tests. One is the t test, another is f test. So, t test is basically gives rise to what you call an individual analysis of a parameter. That means suppose if I want to know whether xk variable, that means suppose there is a variable which is kth variable of independent variable. So accordingly, whether that is kth variable is affecting my dependent variable or not, then accordingly my hypothesis will be the bk, which will be the coefficient of xk, whether it is 0 or not 0. If you can test with the help of t-test, and t-test can be understood that whatever will be the coefficient that we can generate, we can estimate divided by its corresponding standard error. So that's why lower is the standard error, higher will be the t-test. Higher will be the t-test, better will be your what you call the coefficient. So accordingly, you can reject the null hypothesis or accept the null hypothesis. That can be easily taken care of. So what happened over here? So null hypothesis indicate that your beta k, bk is equal to 0, and your alternative hypothesis is not equal to 0. So whenever it is not equal to 0, not necessarily indicating greater or less than 0, then accordingly it gives rise to something called two-tail t-test. If it is greater than 0 or less than 0, then that will give rise to one-tail t-test. Uh, Again, there are a lot of versions of hypothesis testing. So what you are ultimately focusing is that suppose the corresponding bk p value is found to be less than 0.05. So in that case, what we can do, that we can reject the null hypothesis. So that means bk is equal to 0 is ruled out. And when bk is equal to 0 is ruled out, alternative hypothesis will be will be considered to be true. And accordingly, what is your inference, that the xk variable will be affecting the dependent variable, and xk variable is not independent of the dependent variable. That means any increase or decrease in the kth independent variable, that is going to affect what you call the dependent variable. And if your hypothesis testing gives rise to the answer that you have to accept the null hypothesis, then in that case, the interpretation is that the kth independent variable is actually not contributing to the dependent variable change. Dependent variable may be a function of any other variable, but definitely not a function of the kth variable. So that is the idea of t-test over here. Now moving to the next concept called f-test. The f-test idea is that instead of asking for b10, b20, bk0, etc., whether all the variables, whatever may be the 3 variable, 4 variable, 10 variable we have taken into our consideration, whether they jointly affecting our dependent variable or they are not affecting at all. So that is the idea of considering the f-test. And when you club them together and say that the null hypothesis is that all the parameters, they are equal to each other and equal to 0, then that is the framework of f test. And for the f test, there will be two types of ratio will be there. The estimated figure, that means the predicted values figure. Yes, any
Vandana,
question?
please, Vandana, please unmute mute yourself. Vandana Mishra, yes, continue, please.
Okay, sir. Thank you. So that is the idea. That means F test basically this is a ratio of two further ratios. So what you call this is the predicted values series. When you find out the predicted value series and get a square of it, and then deflated it with respect to the degrees of freedom, and then the residual sum of squares are deflated with degrees of freedom. The ratio of them together, they will give rise to F. Anyway, by narrating all those stories, it may not be give you any impulse right now that I can understand. So briefly, within 2 3 minutes, I will switch over to my Excel analysis, so that all those things that is already discussed right now, they will be better understood when you get some data and actually do the things analysis. And then if you can bring them together, then along with the concepts, the idea will be more clear. So I'm not going to details part of this. Basically, this is the goodness of fit argument, etc. They have the technical process of analyzing it, but I think now it is time to go to the Excel file and do some exercise for you, so that whatever we are doing this exercise, how relevant they are, or what is the meaning of it, it will be getting clearer. So I'm just keeping it right now, and if required for the further clarification, then we'll be proceeding here. So the third point, which is the actually the starting point of
Because,
today's discussion,
is it,
is that
because if possible that if suppose so far whatever you have discussed, if students have any clarification in questions, you just look at the chat with also some questions are
okay?
there. Also they can unmute yourself and ask questions. If you have any question before go to this Excel sheet, please.
Okay, sir. Okay. Yes. Is there any chat
Question.
over here? I mean,
Above.
can anyone read
Sir,
one or two for me?
yes, sir, sure,
Yes,
sir, I'll
please
read it.
ask question. Please.
So the first question was asked by Kanupriya Thakur. Sir, like I have dependent variable that is equal to performance related parameters like number of research papers of faculty, then another parameters is feedback, responses of students and pattern number of any, and my independent dependent variable is diversity, perception of faculty and like itself. So which type of regression should be applied? Shall I repeat, sir? So on
No,
the
I need to
right
read.
side,
I need to read that. Otherwise, it will not be possible on my part to understand anything out of it.
on the
So,
extent of right
start
side, there
section.
is a drop down. Go to the right side bottom
Okay,
section.
okay.
Yes,
Yes,
please.
yes, I got it. So, Kanupriya Thakur, right? So, sir, like I have dependent variable performance related to parameters like number of research papers of faculty. Then another parameter is feedback responses of students and pattern number. And my independent dependent variable is diversity perception of faculty on Likert scale. So, which type of regression should be applied? Uh, Even if I have not that much clear with respect to how many variables are there, whether the student is present right now, uh, Miss Kanupriya Thakur, is he available?
Anupriya, if you are there, just unmute yourself and speak, please. Anupriya is not there.
Okay, so in that case, whatever little bit understood. So see, to give specific answer to specific queries like this, it depends on the nature of the variable. Parameter is not important over here because parameter related informations will not be available. First of all, informations will be available with respect to the variables. So now, depending on the nature of variable nature can be ordinal in nature, the variable nature can be numerical, the variable nature may be binary like 0 1, gender, caste, kind of thing. So depending on that type of nature of variable, we have to consider which type of regression mechanism we have to adopt. Number one. Number two is that the same logic can be applicable for the dependent variable also. Like for example, if the dependent variable is a normal variable, like for example, suppose you have a price index or maybe some performance index, like kind of thing, where the continuous variable is available, there is no restriction in it, whether it is varying from 0 to 1 or 100, 1 to 100 or something like that. It is normal variable. What in the right hand side variable, the variable may be something like gender or maybe ethnic group, which can be categorized as 0 1 or maybe 1 2 3 0 kind of stuff. So in that case, the logistic or the what you call discrete choice modeling will be the appropriate modeling. Now, where the dependent variable is not, I mean, dependent variable is binary or 0 1 or 1 2 3 category kind of thing, and the right hand side variable is normal one. If you go for the left hand side variable to be the normal continuous variable, either in ratio format or maybe any continuous variable, but the right hand side variable will be in between 0 1 kind of thing. So in that case, we have to adopt the dummy regression kind of analysis. If the nature of variable will be scaling and both the variables are scaling, then there will be some other type of regression like probit modeling or tobit modeling will be the subject matter of discussion. So to speak exactly which model is appropriate in which context, it will not be that easy unless until we have understood the nature of the variable. So that maximum thing I think I can speak right now, because anyway I have not covered those type of regressions currently. So it will not be right way on my behalf to say that the logistic will be the appropriate model for you or something else, because that is not covered in our discussion currently. I hope that will be sufficient for the student right now. But if she needs some further elaboration or on any aspect of logistic regression, or maybe what do you call any related to any dummy variable related regression, then we can discuss it to the end of the discussion, towards the end of the discussion. Next thing. Okay, one is with respect to appreciation. Thank you very much. The next one is what is the difference between autocorrelation and multicollinearity. Yes, we'll discuss in detail. Currently, I can just tell you that autocorrelation problem is associated with error term. Multicollinearity problem is associated with the independent variable. So whether independent variables, they are related with each other. For example, y is a function of x1, x2, x3. Three variables are there, whether x1 is interrelated with x2 or x3, or x2 is interrelated with x1, x3. On that basis, multicollinearity problem arises. Whereas autocorrelation problem is no way related to the independent variable, rather that is related to error term. Whether error term is 1 year's error term, that means suppose in we have a time series data from 2001 to 2024, we have 24 observations. On that basis, 24 error terms will come. So if 2024 error term is interrelated with 2023 error term, and similarly 2023 error term is interrelated with its previous year, 2022 error term. So in that way, the error terms are correlated with each other in a auto format. That means with respect to own error term, they have a autocorrelation relationship. So that is the fundamental nature of autocorrelation. How to detect it, how to solve it, that they are subject matter of discussion. Maybe after a couple of minutes, we'll be in a position to cover them. Next is how to find out optimum number of covariates. Optimum number of covariates will also be covered to the end of it, because it depends on how many independent variables are there, whether it is 10 should be appropriate one, 5 to be appropriate one. There is a method called stepwise regression also there. So I have a slide with respect to that. So once we'll be covering them, we'll be in a position to clarify it. All those points, I think they can be easily taken care of just after 15-20 minutes if you have little bit patience. Should we further proceed, sir?
Yes, yes, you have to go ahead. Go ahead.
Okay. Okay. Thank you, sir. Is the screen visible now?
Yes, sir.
Okay. Okay. So finally, let us come to the what you call the execution part. So to give you little bit background of this Excel, or to execute the simple or multiple regression, the thing is that like geography, the analysis or the understanding of map is very important. Like normal economic theory, diagrams are an inseparable part of it. In the similar manner, for understanding any what you call regression or econometric exercise, some hands-on I mean experience with respect to any software, that will be a value addition. Otherwise, you may get an idea theoretically, but where to fit, how to fit, there will be problem for that. So, giving that thing in mind, let us start with a simple regression thing in Excel. So that table is already given with you with respect to this slide. So what happens over here? I'm not starting with a very rigorous, what you call, economic theoretical framework related regression analysis. Rather, any normal thing. For example, there are 8 versions of automobiles are available, and those 8 versions of automobiles, they have different weights and they have different mileage. So objective is that if mileage will be considered as a dependent variable, then whether weight of that particular automobile is actually affecting the mileage or not. If yes, then what is the nature of its effect? That means higher is the weight, more will be the mileage, or less is the weight, more will be the mileage. So in that way, if that is the objective of my discussion or objective of my investigation, then how do you decode that thing in terms of our analysis? So we have to find out which one is the dependent variable, whether mileage is a function of weight or weight is a function of mileage. So here there is a problem arises. That means it is completely on the basis of our reasoning. Sometimes the what you call the econometricians, they say that econometrics or econometrics analysis will be futile unless until there is an economic theory. I will little bit modify that spirit by saying that economic theory is not necessarily given by some Nobel laureate and say that this is the sentence where there are 3 4 variables, they are related in a given framework, maybe law of demand, consumption function, or something like that. They no doubt they play a very important role. But even if there is no such existing theoretical or law exists, still then, on the basis of our own reasoning, if you want to find out some kind of testing, then that is also that should be considered to be as relevant as any law or theory. So that's why there is no such a meaning by saying that weight is a function of mileage. Higher is the weight, I mean, mileage is more, on that basis, weight will be more or less. That type of analysis is not relevant. What I'm trying to say is that which one is the dependent, which one is the independent, if it is non-known to us, it should be known to us before a researcher, because it depends on our research objective or question. On that basis, if you rearrange them as x to be y, y to be x, executing in Excel or any other statistical software, you will get some number, you will get some answer. You will be in the similar way of interpreting the result, but ultimately that will be a futile one, because we do not know principle or philosophy wise which should be depending on what. So keeping that thing simple, I have mentioned that suppose we consider mileage is a function of weight, and accordingly the econometric specification will be y is equal to beta 0 plus beta 1 times x plus the epsilon term. Epsilon term is here, suppose the error term. Now what happens over here, if you can go to the Excel file, is the Excel file, can be seen to all of you?
Yes, sir.
Is the Excel sheet is visible?
Yes, sir.
Okay. Thank you. So now what happened? Don't concentrate on this part. Anyway, this is already done by me. So let me first of all delete this analysis. So now what happens over here? We have some year of observations still available from 98 to 2017. So almost for 20 years, 2 variables are mentioned over here. Y is the dependent variable and X is another independent variable. This is another example, I guess. Let me come to the same example that we have seen in the PPT so that it will be better for us. So what happens over here? This is the same table, auto 8 and weight and mileage is available over here. So first thing is that we have to see in the Excel file whether there is a section of data analysis in data or not. So so in the home button, you have to first check, go to the data section. In the data section, there will be a data analysis component should be visible. If it is not visible, we have to first install it. Let me give you 1 minute extra time for that. If you have not that, then accordingly go to the home and go to the option button. Within the option button, there is a section called add-ins. In the add-ins, there is a section called what you call Excel add-ins over here, manage Excel add-ins. If you go to Excel add-ins and go to go, then there are three, four things will come. Solver add-in is another one, analysis tool pack is one. So you have to select the analysis tool pack. If it is selected, then accordingly it will be visible here. If it is not selected, then accordingly it will not be visible. So suppose you are not getting it, then this is the way in which you can generate or you can get an access to the data analysis component. So because in my Excel sheet it is already there. If it is not there, then you can click it and then OK it. So ultimately the data analysis will come. So this is the
Good
first step
afternoon,
for
sir.
MS Excel.
Good afternoon, sir.
Sorry.
Can you please repeat this
Yes, sir.
step again?
यस सर और एक बार
Okay.
बोल दीजिए सर स्टेप वाइज
Okay. So first thing is that in the data section, whether data analysis is visible or not visible. If it is visible, stop because everything is there. If it is not there, then go to file. Step one, file. Step two, within file, there is a section called option. Second option is option. Within file option. Third version, within option, there is a concept called add-ins. Third, step three, select add-ins. After selecting add-ins, step four, go to the manage component. Within the manage component, there is something called Excel add-ins there. So if it is not Excel add-in, then find whether the Excel add-in is selected or not. There are several other versions are there, so you have to select the Excel add-ins. Once Excel add-ins is there, then go to fifth step, go to go. You have to press the go button. Once you press the go button, the add-ins framework will be open. And sixth point is that select the analysis tool pack. If it is already ticked, then data analysis will show. If it is not ticked, then data analysis will not be shown. So if it is not shown, select it. And then seventh one is press OK. If you press OK, the data analysis component will be available. Is it clear?
थैंक यू सर
Okay. Again, for a last thing, go to File, next option, third add-ins, fourth manage Excel add-ins, fifth go, sixth select analysis tool pack, seventh OK. So then data analysis will come. Okay. So if data analysis is there, so what you need to do, you have to uh, uh, open the data analysis. Once you open the data analysis, there will be several analysis tools are there, like ANOVA, single factor, two factor, many things are there. Because our objective is to do something called regression. So if you can go a little bit down, because they are arranged in alphabetical manner, so you select the regression. Once you select the regression, then press OK. Is this step okay till now?
Yes, sir.
यस सर
Okay. So once you open the regression component, then the regression window box will open. The regression window it asks for inputs and outputs. So there is an input called Y range over here. So you have to select this bottom over here, which is like this. So select it. So once you select it, it asks for that which one is the dependent variable. So from the weight onwards till the completion of this, you have to scroll it and leave it. What you need to do, let me tell once more. So you have to in the Y range, you have to select this, you have to press this button, then from weight put the cursor to the weight and then drag up to the 2600, because that is the last digit in that series, because we do not have more further series. So don't select the entire column, only select that particular element which needs to be there. Second thing is that whether you add weight or you leave the weight, it is completely up to us. If you add weight, then there will be no problem. I will tell you why. Because if you drag and select now, then this will be available with respect to the Y range. Then for the X range, the similar manner, you have to go to what do you call the thing. I'm sorry. I have to select the Y range as the mileage. I'm sorry. The mileage should be the Y range. So mileage should be considered as over here as the dependent variable, and the independent variable X range will be selected from weight to till the 2600. So then you have to see whether everything is available or not. As you can see, the C2 to C10. So as you can see here the C2 is from the mileage to C10 is 28. This is the Y range, which is the dependent variable. And in the X range, it is B2 to B10. That means from the B2 weight to B10, 2600, it is selected. The dollar sign, it is actually only freezing the element and nothing else. Then there are different things will come. So if you add label, that means the weight and mileage will be considered as label. If you have considered from 2100 to 2600, and if you have considered from 35 to 28, then the label need not to be selected. If you include the heading of it, then only select the label. If you have not included the heading, then don't select the label. Then it will ask you that where the output needs to be demonstrated. So for that you have to select the output range. It can be asking for in the same sheet or maybe in some additional sheet. So what you need to do, suppose I want to generate the answer just near to my Excel file. So I select a F2 as my area where the output will be shown to me. And then if I go back to my previous case, everything is available to me. If additionally residual needs to be demonstrated, then you can select them. Otherwise, if the residual is not necessary, then you do not put the it. Let me execute it without residual. Then let me again execute it with residual. Then we can see that what will be the value addition of selecting the residual variable and not selecting the residual variable. So let me go ahead with it and press OK. So if you press OK, then what happened? The summary output is available with me. So the summary output indicates that. So there are basically three versions of it. Any regression analysis in Excel will give you a regression statistics like this. This is part one of the story. Second, it will give you a analysis of variance table. The second part of the story, if you want to highlight with some color, then this is the yellow color will be the second part, which is analysis of variance. The regression statistics will be, suppose, give rise to another what you call some other type of color. So this will be the first part of the regression analysis, and the third part of the story is this part of this. So suppose I want to highlight it with respect to some other color. So this is the part. So these are the three part of the regression result. So if you have some data, two variable, and then two variable need to be specified, which one is dependent, which one is independent. Accordingly, if you plot it, then the way in which we have done it, let me do it again for you so that you can understand what is the way of doing it. So if I go to data, in the data analysis, go to regression, which is by default selected. If not selected, then select regression. Otherwise, it will pop up with something else. Then OK. Once the regression window will open, then you have to declare that which one is the dependent variable. This is the dependent variable because I have done recently. So that's why it is showing as it is. Otherwise, for the first time, you have to declare it the way in which you design it. You want to design it. Then for the X range, it will be this particular thing will be your X or the independent variable. Then go to the next thing. Sorry, it is not the X range. This is the X range. Then output range. Suppose now this time I want to generate my output range somewhere here. I have selected this. Again, go back to this. Now, suppose I want to plot my residual. I want to know that what is my residual value. Residual means the error term, basically. So if you select the residual now and now click OK. So what happened? You are getting the same table which is available previously. In addition to that, what you can find, the residual output is generated over here, where you can see, where you can find This is your predicted dependent variable, which is y hat basically, and this is the residual term. And as you can see that the residual term is somewhere negative, second term negative, third term negative, fourth is found to be positive, fifth is found to be positive. And if you go for its sum total, as per your OLS property or the CLRM property, the residual term should be sum total of it should be identically equal to 0, because there is some negative value, some other negative value, some positive value. So if you add them together, you should be getting exactly equal to 0, or maybe very close value to 0, because these are very what you called after decimal. The elements are up to 5 digit or 7 digits. So accordingly, sum total of it. If you want to get an idea, then do one thing: go to let us sum total it, then see what happens. So go to home, and there is an auto sum over here. If you click over here, then you are getting this particular number. This particular number, it is very difficult to understand that what is the value of it. So what we need to do, you have to control C it, paste somewhere here, paste somewhere here, paste some special called some values of it, then click over here. Then what happens over here? If you get the figure, this will be e raised to the power minus 15. So that means this particular number, you have to go to 15 decimal to the left of it. That means before 7, go to 15 decimal. That means it will be 0.00000000. So up to some number, then it will come 7105 something. So that means the value is not exactly 0, but very close to 0. So accordingly, you can consider it to be the residual value, sum total of residual value is approximately 0. Because it is approximately 0, because we are going for a very high versions. If you make them after 2 decimal, after 3 decimal point, then if you go for it, then it will be coming around to be almost equal to 0. So that is the idea of how to do a simple regression analysis with the help of MS Excel. If any doubt exists over here, then please ask me. Interpretation part, I will be just
सर ये
telling you
पेज से वो
shortly.
वाला सेकंड पेज कैसे आ गए सर?
Which one?
सर इस वाला पेज से वो नेक्स्ट पेज स्क्रॉल करने से आता है क्या सर?
ये वाले से
यस सर,
ये वाला.
यस सर.
This is actually pasted a little bit lower to it. So whenever it is asked that where do you want to show your output table, so in that case I have shown it that I want to show my summary output in this case. That's why it is showing over here. So if you want to if you want to select like Q1 is my output to be shown, then it will be shown somewhere in this domain. Here the result will come. Because in the second time I have selected something called B21 as the cell where my output needs to be shown. That's why it is showing somewhere here and down. And in order to get it, you have to scroll little bit lower to that. Is it okay?
Sir, can you
Sir.
interpret the result if possible, sir?
True. The interpretation is the important thing, not the doing the Excel file. So I'm going to that part. So far as the process is concerned, is it clear? How to
Sir,
execute it in MS Excel?
So can you repeat the last step of where you are able to find the zero value, the residual auto sum after that?
Okay.
Ah.
So this particular portion indicates that it is okay. Let me do one thing. Let me copy this part, Control C part, and paste somewhere here. Okay. So I want to go to paste special values over here. Okay. So this is the residual part, which is exactly the way in which we are getting. I'm just putting it over here. Next thing, what I need to do, suppose I want to do it after the decimal, I want to reduce it. After 3 decimal, will it be okay? If I'll do it, are you getting it? How come the number is reduced after 0.551? There is two
So, yes,
options
sir.
in the number over here. If you select this increase decimal, then it will increase the decimal. If you go over here, then there is a decreased decimal, and if you click on it, then it will go for after 3 decimal, after 2 decimal, and kind of thing. And suppose I go up to 2 decimal point, then this figure will be same as this one. Only thing is that I have reduced it to 2 decimal point. Why I am
Yes,
doing
sir.
is that because now if I go to and get a sum total of it, auto sum kind of thing, I am getting 0. Are you getting it? That is the point I want to highlight over here. This figure is again approximately equal to 0. This figure is exactly equal to 0 because after decimal, I have gone up to only 2 decimal points. So many things are what you call adjusted with each other, because the figure with respect to the number 1 is not 0.55. Rather, as per the figure over here, it comes to be minus 0.55102. That means if I allow for 5 decimal after decimal point 5 points, then accordingly this figure will be a specific one, and this is the general one. And that's why adding them together, it will give rise to the value 0. And same thing is that if you add them together, it will give you also a value 0. Though we are not getting 0 because there is a what you call after decimal, we have allowed for some numbers over here. That is the thing. Anything else? No, I
Thank
guess.
you, sir.
So in that case, okay. So in that case, let me go to the Excel file and let me try to help you to understand the regression output so far as we have done till now. So this is the calculation part, and I have deliberately done it for you so that it will be easier for you to understand the interpretation. See, whichever software you use does not matter. Whichever way of calculations you do, whether you do it manually, whether you do it along with any advanced version of any software packages, ultimately, whatever the result it will give you, whether you are in a position to understand and interpret it properly or not, that is the important thing. Otherwise, it will be same as playing a video game without understanding the nuisances or the idiosyncrasies of the video game. So software modeling is similar as that of a video game thing. It will not give you any thing more in comparison to only the first calculation part. But whatever the calculation part is done, now the next part is that how to interpret it. Now we are getting the same thing. First of all, if you have any doubt, then just cross check with the finding over here. Which one is highlighted over here? So multiple R 0.91, R square 0.84, adjusted R square 0.81, ANOVA regression degrees of freedom 167, SS 134, 25, etc. This figure and this figure, whether they are same or different. Hello? It
Yes,
is
sir.
same or
Same is there,
different?
sir.
Same.
Is same,
Okay,
sir.
thank you. So now moving to the interpretation part. So what happens over here? So as we can see, first thing is that our hypothesis model is Y, which is your mileage, is a function of weight, and this is the econometric specification. Now what we do, we estimated the equation, and for beta 0, we have found out something called B0. Now this B0 is your estimated coefficient. Beta 0 is what you call the normal or the actual coefficient. And now this B1 is your what you call estimated coefficient of this beta 1. That's why this is what you call estimated model, and this is what is your actual model. In the actual model, there is a error term component. In the estimated model, there will be no error term because as we have seen, on an average, the error term will be equal to 0. So that's why there is no mention of estimated value. Now the original variable will be y plus this y hat plus epsilon. So that means if you replace it with respect to y hat, then it will be y is equal to y hat plus epsilon. And that's why this thing is coming around over here. If you pay attention in this part, so this is nothing but this y hat, and this is nothing but your error term. So if you add them together, whatever the value comes out to be, that will be exactly equal to this mileage called 35. Just pay an attention, 35.55 something plus minus 0.55 something, it will be equal to 35. Second point is that 30.23 something plus minus 3.23 something, it will give rise to something called 27, which is the figure over here. So this is the exactly the way in which we have done over here. So this is what is called regression output. 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 So this is this y is equal to y hat plus epsilon, and y hat and epsilon figure has been demonstrated you with respect to the second version of the model that we have done. Now, coming to the interpretation part, these regression statistics, they have five components over here. One is the multiple R. This multiple R is nothing but the correlation coefficient between the two variables y and x. So before regression, we should be targeting for the correlation analysis. That means whether there is a causality, causal effect association, or they are just moving in a given manner. So what we get an idea that there is a 0.9176, because ideally the R value, which is correlation coefficient, it will vary between -1 to +1. +1 means it is perfectly collinear. Perfectly collinear means two variables are very high degree correlation exist. And if it is very close to value like this in which we are getting it is plus 0.91. That means y and x, they are moving in the same direction. Higher is y, higher is x, more is y, more is x, higher is y. That means x and y, they are moving in the same direction. In other words, weight and mileage, they are moving in the same direction. Higher is the weight, more is the mileage, more is the mileage, higher is the weight. That is the point one, and 0.9176 indicate that there is a high degree correlation exists between the two variables. Second is that so far as the R square is concerned, R square is something called coefficient of determination. That is exactly the goodness of fit. That means how good is your model is. The model that you fit, how far it is good. Obviously, it has also a limitation. Limitation is that the R square value is also maximum can go to the value 1, and very close value to 1 will give you an idea that your model is good. If if it is far away from 1 and close to 0, then your model will not be good. It will be considered as moderate, or maybe poorly fit or something like that. So that is the idea. That's why we are getting 0.8420. 0.8420 is basically nothing but the multiple R square. So this is R 0.9176. If you square it together, then you will give rise to R square, which is the coefficient of determination, which will give you an idea that how good your model is. Close to 1, good fit. Less than 1, and as it will be fall from 1, 0.61, 0.51, 0.41, your goodness of fit will be less and less. And on that basis, you can say that your model fitting is not that much appropriate, because you have managed to explain 84% of your actual variable through your fitting variable. That is the interpretation of something called R square value. Now coming to the adjusted R square value and R square value will be more or less similar. Only difference between here is that adjusted R square will be a deflated value of R square. In the simple regression model, there will be hardly any difference, because adjusted R square value depends on the degrees of freedom, which is based on the parameter. And the parameter will be 1, 2, 3, 4, etc. So on that basis, it will be varying. It will be varying in the sense that if you have multiple regression, sample size is not that much large, then accordingly adjusted R square and the actual R square value will be different. Otherwise, they will be same. If you want to get a proper idea with respect to the adjusted R square, that's why I have not gone into the details of it. Then the adjusted R square value interpretation as per our slide is somewhere written over here. The adjusted R square is used to compare two or more regression model that have the same dependent variable but differing number of regression. Since the adjusted R square is usually smaller than unadjusted R square, it seems it imposes a penalty for adding more regression to the model. That will be not a problematic situation currently, because what happens over here, that we have only gone for two variable, where one variable is dependent, another variable is independent. That's why the degrees of freedom problem is not very much what you call visible over here. There is a marginal effect on adjusted R square, and always adjusted R square will be less than the actual R square value. Now coming to the standard error component indicates that it will be basically the square root of what you call the mean square of error. And what is mean square of error, that will be clear with respect to the second part of the story, which is ANOVA. And ultimately, we have gone with the 8 observations, and the total observations is mentioned over here. So this is the first part of the story where the standard error component will be discussed with more clarity now. Now coming to the ANOVA part indicates that there are three parts of it. One is the regression part, where the regression part, the degrees of freedom, it is basically k minus 1. K means parameter. Here there are two parameters, beta 0 and beta 1. Or in other words, there are two variable. One is dependent, another is independent. On that basis, k is 2. K is either beta 0, beta 1 or x and y. So because two variables are there, so accordingly 2 minus 1, the degrees of freedom is 1. Residual error term, the residual error term degrees of freedom is n minus k. N minus k means number of observation, which is 8. K is number of parameter, 2. So accordingly, 8 minus 2 will be degrees of freedom 6. And total will be 1 plus 6 will be 7. That will be the matter of discussion. Now coming to the sum of square, the sum of square over here, what happens over here? The sum of square, and accordingly on the basis of the sum of square, we have find out the mean sum of square. The sum of square is nothing but the predicted variable, whatever is the predicted variable over here. If you add them together, if you go to somewhere here, and accordingly in the Excel file, if you go to this part of it, find out its square term, generate another point over here and find out its square term over here. Let me do that part thing for you. Equal to bracket start this part, raised to the power 2, bracket close, end. Now if you add them together, this is the entire sum of square. This sum of square, if you want to find, equal to sum of it, sum total of it, bracket close, then this becomes 9382.71. This 9382.71 uh, uh, sum of square. This is what you call. This will be something related to that. I have forgotten that process. This is not actually the sum of square value over here. Some portions of the sum of square will be this 134.72 divided by the degrees of freedom. This is what is called the mean sum of square over here. And similarly, this error term over here, this 25.28 divided by 6 will be this 4.21 as the mean sum of square over here. And this F statistics is nothing but the ratio of these two, 134.72 divided by 4.1. And this is what is your F statistics. And this is the p value of that F statistics. The p value of F statistics indicate that, as usual, if the p value is less than 0.05, that means 5% level of significance, less than that, then your F statistics is found to be significant. So in the other words, it indicates that this ANOVA analysis is broadly indicating that inclusion of this X variable is playing an important role in affecting Y, and that's why you cannot say that X is not affecting Y. X is not affecting Y, that is the interpretation of the second part of the regression analysis. But exactly the effect of X on Y, that can be understood with the help of the third part of the story. The third part of the story indicates that there are two variables over here. One is the beta 0 intercept term. The beta 1 is the weight term. The beta 0 intercept term is B0. So B0 found to be 72.77. And the weight variable comes to be B1 is found to be minus 0.01. Remember, the correlation coefficient indicates that there is a positive relationship between the two variables. Higher is the weight, more is the mileage. More is the weight, higher is the mileage. And the degree is 91% almost. But coming to the regression analysis, what you can see that if the weight of a particular automobile increases by a particular unit, whatever may be the unit in LBS or whatever, then accordingly it is affecting the mileage in a negative manner. That means weight is affecting mileage, but it will be in negative manner. By the way, negative or positive, whatever will be the subject matter, they are subject matter of interpretation if you go to the respective T statistics. The T statistics indicates that coefficient divided by standard error is T statistics for intercept, as well as coefficient divided by standard error will be the T statistics for the weight slope term. So accordingly, what happened? The p value, again the same logic. If it is come to be very close to 0, it is good. and accordingly the t statistics become significant. Once the t statistics become significant, you can say that the variable is affecting the dependent variable. But the way in which they are affecting, they are subject matter of discussion with respect to the sign. If the sign is negative, then weight is affecting mileage in an inverse manner. Higher is the weight, less is the mileage, and less is the weight, higher is the mileage. Next point of interpretation is that if weight is increasing by 1 unit and the unit is measured in terms of LBS, I guess, then accordingly, if there is a 1 LBS weight increase for any automobile, then accordingly the mileage will be reduced by the zero point zero 0.01 unit. And that 0.01 unit, for that unit, if you go to the Excel file, the units are measured over here, the mileage in mpg and the weight is in lbs. So accordingly, if there is a 1 unit 1 lbs unit increase in any of the automobile, then that gives rise to 0.0177, uh, what do you call, the unit is now is the LBS. So accordingly, it is affecting the LBS by zero point zero 0.01 unit. 0.01 is the reduction of it. And in that way, we can interpret that weight is affecting to the mileage in an inverse manner. So this is the idea of T statistics, which indicates that individually how the X is affecting the dependent variable, jointly how the X is affecting to the dependent variable. Hardly there is any point of difference between F and T assessment so far as a simple regression is concerned, because X is no way associated with any other variable. So joint association does not make any sense over here. But still then, for the sake of completeness, both T and F found to be positive and T is found to be negative. Accordingly, we can say that X is affecting Y and X is negatively affecting Y. That means higher is X, less is Y, and the value of 0.01 will give you the interpretation in the manner. This is the standard way of interpreting the result. If you have any doubt with respect to the interpretation, please ask me. Any question at this point of time?
Sir, good afternoon, sir. Sir,
Yes.
here, sir, R square is there. R square like 0.84, like that is there. So here, any ranges is there, sir, like goodness, like that, which range is good, this R square?
See, theoretically speaking, the R square value, as I have shown over here, it will vary between 0 to 1. It cannot be more than 1. It can maximum be 1. It cannot be less than 0. It can be at minimum 0. So any point in between 0 to 1 is the value of R square. Now the next
Sir,
thing is that if the R square, yes.
sir, my doubt is here. For example, 0.54, like that, 56, or like
Okay, any
0.64,
specific case
like,
basis. Okay.
sir.
See, again, that answer is also subject to many other things. Frankly speaking, higher is R square very close to 1. That should be good. That should be good, may not be necessarily good. So always remember that if it is varying between zero point 0.6 to zero point 0.8 or 0.85 kind of thing, again, there is no such rule of thumb. But broadly speaking, if it is zero point 0.6 to 0.85, zero point 0.9 kind of thing, then there may be a sense that it is a good fit. But if it is less than zero point 0.6, then there is a possibility of recheck whether your model is good or not. If it is more than 85, 0.85 or zero point 0.9 above, then though it seems to be good one, but you have to be very suspicious with respect to your result also. I should not speak these things right now because we are at the very beginning part of the R square analysis. So at the beginning, it should be a high good, less bad. But always high good, that is not a universal term. If it is found to be something called 0.99 or 0.98 kind of thing, then that R square value should be looked at with a suspicious eye, because there may be something, some specification or some other type of problem because of which your R square value may be found to be very inflated one. So that is also not a very good sign. Very high or very low is not good. Like the case in which we understand the concept of obesity, if a particular person is very highly weight maybe 100 kilogram above or something like that, then in that category also that will be a malnourished person. If I'm not wrong, the health economist may correct me. So there are two types of malnourishment. Not only those who are very less in weight, very high in weight also, they come under the malnourishment category. Maybe category 2 type or category 1 type exists. But anyway, very high weight is also not considered to be good one. In the similar line, very high R square value may not be considered to be a very good indicator. We have to be suspicious. Why and how so will be get to know in our subsequent slide. We have explanation for that.
Thank you, sir.
Sir, can you again explain the standard error interpretations and the B1, sir, B1 value that is minus 0.0177, sir?
Okay. So minus 0.0177 indicates that, see, interpretation of any regression, it depends on whether you do any kind of functional form arrangement or not. Currently, we have not converted the series to any logarithmic or anything else. They are with unit. That means they're unit loaded, not unit free, number one. So when you say unit loaded, what we need to do, we have to first check whether the t statistics is significant or not significant. What is the way of doing that analysis? We have to see the corresponding p-value, whether it is less than 0.05 or more than 0.05. If it is less than 0.05, like the way in which it is 0.0013, which is less than 0.05, your corresponding t statistics is found to be significant. Whether whatever may be the sign, positive, negative is not important. Anyway, negative is coming because your coefficient is negative, because any statistic, t statistics is nothing but the coefficient divided by standard error. Now you can understand why we have put so much time and effort in understanding the standard error component. If the standard error will be very high, then accordingly the t statistics will be very low. If the t statistics will be very low, then the p-value will be corresponding to that will be greater than 0.05. So in that case, the variable may not be found to be significant. So now, fortunately, we have found the standard error will be very less and the ratio is found to be 5.65, which is very large in number. If you have doubts in p-value, then a rule of thumb indicates that your t statistics for a 5% level of significance should be on an average +2 or -2. That means for any 5% level of significance, if your t statistics is found to be greater than 2, 2 or greater than 2, and accordingly -2 or less than -2, then accordingly your statistics should be significant. And that's why we are getting minus 0.65, which will be very less than -2. In case of positive, like the way in which it is in the above category, it is found to be 10.55. So accordingly, it some seems to be furthermore what you call significant in nature. So that is the idea in which we interpret whether the significant or not significant. If the statistics is found to be significant, then only we can go to the sign, whether sign is positive, makes sense, or sign is negative, makes sense. If the value is whatever may be the value, and the statistics is found to be insignificant, that means it will be lying between -2 to +2 category, any number. Again, -2 and +2, they are just rule of thumb, because exactly 1.96 is the exact value. But anyway, suppose as a rule of thumb, -2 to +2 category, then in that sense, the significant level will be subject to discussion. So accordingly, what happens, this may not be significant, and whether the sign is positive, negative does not matter. Because now it is making sense. So accordingly, how do you interpret it? If the weight, because weight is the independent variable, if the weight increases by 1 unit, whatever may be the unit, if the weight increases by 1 unit, the mileage of any automobile will fall by 0.01 or maybe 0.0177 unit. So that means 0.0177 unit will be the reduction in the mileage of any automobile if the weight of the automobile on an average increases by 1 unit. That is the way in which we interpret the weight respective coefficient. Is it clear?
Yes, sir. Sir, next doubt is the sir. What is the difference between the standard error which is given in the regression statistics and the standard here which are given in the intercept or the weights put the like here it is 2.0528, but here it is 6.8961 and point 0031, sir.
0.0031. Where it is? Acha, okay, this one. This
Yes,
standard
sir.
error. This is the
Yes.
this is the standard error of this particular coefficient. That means this particular weight. This weight is a variable, right? Corresponding to this weight, if you find out the standard error of it, then corresponding to this coefficient, you have to find out the respective thing. This is a basically mean value of it, and this is the dispersion measure of it. Whereas over here, this particular standard error, this standard error with respect to the regression statistics standard error, which indicates over here that this 2.058 will be a square root of this 4.21. This 4.21 is the error term. This is the residual value, residual series error term. That particular error term is come out to be, that particular square root of it will be coming around to be 4.21. And if you find out its square root, 4.21 square root will be 2.05. So standard error of the error term of this, and this is the standard error of the independent variable of it. So that's why they are the two different things. They are not come under the same category. That's why this standard error will be useful to understand the coefficient is significant or not. But this standard error will be an indicator whether on an average the residual value is playing an important role in the analysis or not. So here the error terms standard error is found to be 2.0528, which is making a sense in the sense that if it will be very high, then accordingly your F statistics will be very less. So that's why this particular value is need to be also as less as possible. Your regression corresponding to regression, that means your fitted model kind of thing, it comes out to be 134.72. So in that way, these are the two different things. These are fitted model. This is for the residual model, and this is for the independent variable. So this is y hat. This is for epsilon or u term, and this is for the x variable. So accordingly, x variable corresponding standard error is the measure of dispersion. This is the standard error with respect to the residual. This is the standard error. This is the standard error with respect to the fitted model y hat. That's why they are three things, because here there are three things over here. X is independent variable, y is dependent variable, and epsilon is the what you call the variable over here. So corresponding to this epsilon, this is the 4.21. Corresponding to this y, this is 130.72. Corresponding to this x, this is minus 5 point, sorry, this is 0.0031. Is it clear?
Thank you, sir. Yes, sir. Thank you, sir.
Excuse me, sir.
Yes, sir.
It's very nice presentation. Thank you, sir, very much. Sir, please, if you can repeat, please repeat what is the difference in between multiple R square, adjusted R square, and R square? As there are only two variables included in the model, and what is the meaning of multiple R square here? And why they differ so much in the data?
Different from data means?
मतलब why they are multiple R square, adjusted R square, and R square? Why they are so much different as there are two variable included in the model?
They are not very different to each other. This R square value is actually very close to a 0.81, 0.84, and 0.81. This 0.84, they will be adjusted with certain degrees of freedom, because of it is come around to be this 0.81. Exactly the formula for adjusted R square, if I recall it properly, the formula for adjusted R square, then this is R square divided by degrees of freedom, and that's why they come around to be 0.84 divided by 0.81. Otherwise, many of the times there is no difference between R square and adjusted R square. Now, comparison to this multiple R, this is not R square, this is multiple R. This is correlation coefficient. So if you square it together, 0.91 or 0.92 square will be something come around to be 0.84. So in this way, this is the correlation coefficient between the two variable. Now, if you find out the correlation coefficient to be this, if you square it, then you will get 0.84. And out of 0.84, if you divided the deflator, which is the degrees of freedom, then you will get the adjusted R square. What happens in the multiple regression? This found to be very different with respect to the R square. As the inclusion of more and more variable, the R square variable will be more and more. So if you have one independent variable, if it is 0.84, if you add 2 or 3 or 10 variable, then it comes around to be 0.98, 0.99 kind of thing. But that may not be a true indicator of goodness of it. That's why if you deflate with respect to the number of parameters and other degrees of freedom and number of observations, etc., then what happens over here? You come around to be this adjusted R square will be less and less, because for multiple regression analysis, this inclusion of more covariate increases R square, and inclusion of more covariates reduce the R square. And this adjusted R square will ultimately a matter of what you call an indicator that after getting so many covariates also, if your adjusted R square value is found to be good one, that means 0.6 to 0.85 that I told you earlier, then it seems to be a good one. Otherwise, if adjusted R square value is very less, then whatever may be the nature of your regression, you have to be suspicious. Very high adjusted R square is also bad, and very low adjusted R square is also not good for the modeling part.
Thank you so much. Thank you so much.
Okay. Anything else?
So which R square is more important, adjusted R square or R square, sir,
Uh,
for interpretation, sir?
for any regression analysis, adjusted R square will be relevant one in comparison to R square, because it will not be a case always that we have only one independent variable. Simple regression is a what you call a very specific, special, or very what you call uh, not a usual case. Any regression, we majorly go with multiple regression that we are going to do right now. Just hold for 2-3 minutes. Once we go to the what you call the next part of the story, then it will be getting clear that the difference between these, how come they will be very high or less when we go for a multiple independent variable. So if you allow me, then let me proceed further and go to a multiple linear regression model. So in the multiple linear regression model, the framework says that there can be two or more than two independent variables. So multiple means at least there must be two or more than two independent variables. So in our case, the current example case, what happened, which is shown over here, in case of in case of this example, where there are four variables taken, and the nature of arrangement is time series analysis. So what happens over here? So there are four variables over here. So what we need to do over here, we have to classify the four variables into dependent and independent category by following certain functional framework. And functional framework, they come from any reasoning. And currently we are taking the economic theory behind it, because we know that if the variables are like consumption, income, wealth, and interest rate, it may happen that consumption of anything will be a function of income, a wealth, and interest rate. And there may be a kind of functional framework like this, that y is consumption, and y depends on x1, which is income, and x2 is wealth, and interest rate is what you call x3. And according to the economic theory, higher is the income, there is a possibility of more consumption. Higher is the wealth, there is a possibility of more consumption. And higher is the interest rate, there is a possibility of reduction in consumption, because you have to pay a lot of, repay back or something like that. So high interest rate may affect the consumption in an inverse manner. So this is the way in which we can, in the very beginning, we have some framework in our mind. And if you want to specify it in terms of econometric manner, then there will be y is equal to beta 0, beta 1, etc. Now you can understand there are three independent variable and one dependent variable, and accordingly beta 0, beta 1, beta 2, beta 3, there are four parameters over here. So accordingly k will be 4, and on the basis of number of observations that we can see that it is varying from 1964 to 2017. So you can calculate what will be the number of observations. So accordingly, k and n is known to us. If it is even not known to us, then let us go to the Excel file to do a similar type of analysis. So let me go to the Excel file now. There is a segment for multiple regression over here. So there are n number of things are highlighted over here. So what let me first remove all those things so that it will be not creating problem to understand the procedures of it. So let me delete them. Okay. Okay, something else is not deleting. It is fine, no problem. If you want to delete it, also no problem. It will create authorized, not okay. Fine. So if you see that these are the same variables that we have shown in these slides over here. So what we need to do, similar manner, go to data. Now go to data analysis to do a multiple regression. First select regression, get OK. Then you have it asking that what is the dependent variable input range. So what we need to do, we have to highlight that consumption is our dependent variable. So consumption, if you select the consumption portion and select over here, then go to again the window for person, select input range, go to the input range now. What happens over here? Starting from income, wealth, and interest, instead of going for one only, now we have to club them together and jointly select it. That is the procedural difference between simple regression and multiple regression. Wherever you want to execute a multiple regression, what you need to do, all the right hand side variables should be available in one way, one go. That means C, D, E, D, E, F, G kind of thing. Then it will be easier for you to select it in one go. And then if you do it and go to the previous version, then as usual you select label because you have selected consumption, income, wealth, etc. If you have not included them, then this tick mark is not required. Because we have considered it, then that's why we have selected the label. Then again, it is asking for output range. If it is output range you want to mention somewhere, then suppose I want to highlight my output range here somewhere and go to the version. Now output range is available, will be available at H2. If you now can see, I have highlight my output to be shown at H2. Then accordingly, I want to demonstrate my residuals also. If you do not want to show your residual or predicted value, then you do not select it. If you want to do that, then do it. It is completely up to your choice. There is no hard and fast rule. And then press OK. Now what happens over here, as you can see in the similar manner previously available, the summary output is giving us three phases of analysis. One is this fetch, go to home, give some set to that. Then this is the second part of the story. Second part of the story is your ANOVA table. So second part of the story is ANOVA related stuff. So this is second version of it. Then coming to the intercept kind of thing, this is the finding of it. So this finding may be kept little bit yellow, and this is the part. Now, as you can see, there is no difference between the first part of the previous simple regression part, no difference with respect to the second part of the simple regression part, but only difference with respect to the third part, because in the first part there is only two term points associated with it, intercept term and weight, because weight is the only independent variable. Now, because we have gone for what you call three variables as the independent variable, so along with the intercept term, we are finding income, wealth, and interest term. That's why we have seen over here this particular value seems to be a bulkier one in comparison to the previous analysis. Otherwise, it will be the same way. Now we can see that your multiple R is coming around to be 0.999701. Second point is R square, which is coming around to be 0.999402. The question which was asked previously, just a couple of minutes before, sir, high R square is good for the analysis. So what is the problem of it? Because it is giving us a threat element. Because as I told you previously also, very high R square value And accordingly, adjusted R square value is also not found to be very different, because even if we have included three variables over here, but they are no way going to affect the adjusted R square value very significantly. So what happens? All those three elements over here, they are subject matter of threat, because there is a possibility of some problem, and that's why the diagnosis related stuffs are required. That is why the fourth part of our analysis is diagnosis, because whatever seems to be very, I mean, green or maybe yellow, yellow is not necessarily gold always, or green is always not necessarily a sign of prosperity. So that's why we have to be little bit suspicious. Whatever may be the result nature, that may be subject matter of diagnosis. That's why the fourth part is very important. And in the similar manner, you can interpret the way in which the interpretation for the other variable. And as you can see over here, the observation is 54. That means we have taken 54 time period and four independent variable, sorry, four variable altogether, one independent and three independent variable. And accordingly, the nature of degrees of freedom is mentioned over here. Significance of F statistics is found to be significant because e to the power minus 80 means corresponding to this, it will be very close value to zero. So accordingly, F statistics is 27,838 point something, which is very high in nature. So jointly income, wealth, and interest. That means income intercept is equal to wealth intercept is equal to interest intercept. Jointly, all the three intercepts are equal to zero. That is the subject matter of hypothesis testing under F. Now it is found to be rejected. That means jointly they are contributing to the dependent variable. They are not independent to each other. That is the interpretation of this F statistics. And for that F statistics, we need MS. And for MS calculation, we need sum of square. And accordingly, degrees of freedom will be, this regression will be 4 minus 1, k minus 1. So 4 is the number of parameters. So 4 minus 1, 3. Residual will be n minus k. 54 is the n. K is 4. Then accordingly, 54 minus 4 is 50. And total will be n minus 1. So it will be 54 minus 1, or it will be simply 3 plus 50, 53. So this is the same part, similar part of the previous one. And on the basis of now, any one of you, if you can help me to interpret the income, wealth, and interest coefficient for me, I'll be very happy. Can anyone help me to interpret income, wealth, or interest value? Whether anybody wants to voluntarily interpret any one of it?
Sir, it means 1% increase in the consumptions. It leads to the
Not percentage.
0.73.
No, no, not
One
percentage.
per
First of all, not
one unit.
percentage.
Sorry, sir. It is one
Yes.
unit increase in the
No, that
consumption.
is no, I'm sorry to correct you, but you have to be very, very attentive while jumping to the interpretation.
Yes, sir. Thank you,
Percentage
sir. Thank you,
increase or
sir.
decrease or unit increase or decrease is a very important part. That is actually my subject matter of further discussion. So first thing, whether it is logarithmic transformed or not, if not, then there is no concept of percentage increase or decrease. So income is measured maybe in terms of rupees or whatever. I'm sorry, I somewhere removed it at the beginning. So I thought that all the variables were mentioned over here. So many things will be in terms of rupees, I guess. So consumption is terms of rupees, income is terms of rupees, wealth is in terms of rupees, and interest is something in terms of percentage. Getting it? Because interest cannot be in terms of rupees, right? So interest is in percentage. Okay, carry on, please.
Uh, yes, sir. As the all the value are the significant value, I think, sir, p values. So we can interpret like this. So, one unit increase in the consumption leads to the 0.73 increase in the income, 0.035.
Please stop, please stop, please stop.
Yes,
Is this
yes, sir.
interpretation correct? Others, please, whether this interpretation is correct. One of our friends says that if consumption increases by
Sir, it is other way around.
0.73,
Sir,
very
it is
good,
other way around.
very good. Thank you very much. It is the income's coefficient. So income's coefficient means if income changes, income is the independent variable. So if the income increases by 1 unit, unit may be rupees, then accordingly there is a 0.73 rupees worth of increase in consumption. In other words, if you want to say, if my income increases by 100 rupees, then there is 73.4028 rupees increase in consumption. Because I do not know whether it is for a district level analysis or state level analysis or maybe one individual's analysis or whatever. So depending on that, whatever may be the information known to us, you can say that whosoever is the respondent, accordingly, if his or her income increases by 100 rupees, then 73.4028 is the increase in consumption. If you are not comfortable in that, just say that if there is a 1 rupees increase in income, then there will be an increase in the consumption by 0.734028. Is it clear?
Yes, sir. Thank you, sir.
Okay. For that, we need to understand that first of all, we have to see from the fourth column onwards whether p-value is significant or not. If p-value is significant, then sign is positive or negative. If the sign is positive and negative, accordingly, whether increase leads to increase, decrease leads to decrease, or increase leads to decrease, and decrease leads to increase. Negative sign indicates that higher income, less consumption, less income, higher consumption. But the corresponding sign is not negative, it is found to be positive. So accordingly, there is a positive relationship between income and consumption, which also makes some sense to us because we know from our fundamental law of consumption by Keynes that there will be an increase in income, then there will be an increase in consumption. And if you remember that what you call the autonomous consumption part, and there is something called what is that? Marginal propensity to consume kind of thing. So what is the value of marginal propensity to consume now? Are you getting it now?
0.73. Yes, sir.
Very
Beta.
good. Very good. So that is the beta value, which is 0.73 now. That means if income increases, then consumption will increase, but not by the same proportion, rather less than proportionately. Isn't it? That is the theory. So now we are getting the number and validate our argument by saying that taking a 54 years observation, we come to the conclusion. Now, in the similar manner, we can interpret wealth because wealth and income, they are in rupees term. So, and they are found to be positive also. So, if there is a 1 unit increase in wealth, then there will be 0.035976 rupees increase in consumption. If you want to increase your income by 100 units, then 100 units increase in income gives rise to 3.5976 rupees in increase. Sorry, not income, rather wealth. If your wealth increases by 100 rupees, then accordingly your consumption will increase by 3.59. How come it becomes 0.0359 to 3.59? Because we started from 1 to 100. So accordingly 0.03, the decimal before 0.03 will now come after 2 decimal point. So that becomes 3.5976. Is it correct? Right? Yes or no?
Yes, sir.
Yes, sir.
And anyone else briefly tell me what is the interpretation of interest rate?
Sir, there is a negative relationship in between interest rate and consumption. As we can see, there is a minus sign in the interest rate. It
Very
seems
good.
a 1% increase in interest rate leads to, sorry, 1 unit, yes, 1% increase in interest rate leads to minus 5.5 rupees decrease in the consumption.
Very good. Completed. You have successfully completed this course now. So you have understood the mechanism of this interest rate and other things. If there is any doubt, then we can further go to any another multiple regression, or if not, then we'll go to the diagnosis part because diagnosis is playing a very important role. So I think we should go to the diagnosis part now because otherwise it will be injustice because this part is okay, fine, but the diagnosis part needs to be little bit time spent. We need to spend our quality time in the diagnosis part. Yes.
Excuse, sir. Sorry for interruption, sir.
No, fine.
There is a high p value, like the p value is greater than 0.05%. So can we say that the model is
perfectly not fitted, as the intercept term is not significant here, according to the p-value. And
For
also,
the intercept part, actually, see, intercept part is what is the value? What is the value addition of this intercept part is that when all the three variables are assumed to be zero, because that is the way in which we interpret any intercept term. So intercept term indicates that the consumption will take the value of minus 20.6328 rupees only when income is zero, wealth is zero, and interest is zero. Technically speaking, are you getting it? That means if the income is not contributing to the consumption, wealth is not contributing to the consumption, interest is not contributing to the consumption, then accordingly, your intercept on value, whatever is the value, that is the what you call figure for consumption, which is found to be insignificant. Why? Because the fee value is greater than 0.05. So accordingly, minus 20.6328 is be considered as zero. Always remember, any coefficient value is not important. Only when it is significant, its value is important. Otherwise, if the p value is found to be greater than 0.05, whatever may be the minus 20.6328, it should be considered as zero. Any number, whether it is plus 100 point something or minus 200 point something, does not matter. Does not matter. It is be just completely equal to zero because the coefficient is found to be insignificant. When the coefficient is found to be insignificant, according to the null hypothesis, minus 20.6328 is equal to zero. In mathematics, it used to be a very absurd analysis because any minus 5 cannot be equal to 0. But we are not saying that it is equal to 0. They should be interpreted in line of 0 because objective is that B0 is equal to 0. Hypothesis is that intercept is equal to 0 or not equal to 0. Because we are finding that null hypothesis is accepted. So that's why B0 is 0. So minus 20 point something is actually 0. That means there is no intercept term. So if you draw the consumption function, then accordingly it should be starting from the origin point. There will be no autonomous consumption component over here. That is the overall analysis. Autonomous consumption component will be zero.
yes, sir. Thank you, sir. Sir, can we consider the level of significance from 5% to 10% that we can have the intercept of minus 20?
Yes, but there is no such p value currently right now. As per our finding, we are not getting anything between 0.05 to 0.1. There are basically three stages of hypothesis testing. One is 0.1 greater, strictly rejected. No way under any circumstances that is significant, like 0.114 right now. Next is second point is that if it is less than 0.1, that means 10% level of significance less, and it is more than 0.05, that means 5% level of significance more, then you may consider it, but with a very hesitant note by saying that it may be significant, but the degree is very less. So if you are, it depends on the nature of your as a researcher. If you want to give only good things in your basket, then don't go for more than 0.05 to 0.1 bracket category. But if you want to keep you as a weak, because see, in other versions of economics also, there are different axioms, like there is something called strong axiom, weak axiom. Something is strongly unequal, something called weakly unequal. So in that way, 0.05 to 0.1 bracket category will be in weakly consideration. But it is completely up to the researcher. If he or she wants to include it, then it may be included, but it cannot be relied upon. On the basis of that, you cannot go for a very strong conclusion. But anything less than 0.05, you can go for a very strong conclusion. Is it okay?
Yes, sir. Thank you, sir. Yes, sir. You can proceed now.
So may I ask you one question, sir?
Yes.
Sir, when we apply multiple linear regression model, so should I test our data like linearity and multicollinearity, heterogeneity?
Yes, ma'am. That's why I mean, before going to doing that analysis, first thing is that diagnosis will be a subject matter of the results obtained, because
Yes,
now
sir.
the result is actually the seem to be very greeny, because R square adjusted R square are very high.
Yes,
Independent individually, the variables are also found to be very good in nature. So if you rely on it or do not rely on it, that is a subject matter of our subsequent discussion. Just wait for 1 minute, ma'am.
okay.
I will give you the answer.
Okay.
Okay.
Okay. Thank you.
So,
Thank you, sir.
because which problem arise, which problem is there, we cannot just trace it on the basis of this information, which is represented here in terms of three-sided region.
Sure.
इसको देख के पता नहीं चलेगा कि कौन सा वाला अच्छा है, कौन सा
Sure,
वाला
sir.
नहीं अच्छा
Sure.
है. That's
Sure,
why
sir.
we need to go for a further analysis. Just
Okay.
hold for a minute or two. I will give you the answer.
Yes, sir. I'm okay.
Okay.
Thank you,
So
sir.
may
So
I
now,
please,
yes.
sir, if we go back, so does the T stat column, does it have any significance, or it is the values are just table values?
uh, they are not table values. See, something, if you ask me, then I'll tell you, there is something called calculated value, there is something called tabulated value. So these values are actually calculated values. So these calculated values need to be compared with the tabulated value. And rule of thumb, tabulated value for any 5% level of significance, t value will be 1.96, either plus or minus, depending on whether it is I mean left tail t-test or whether it is right tail t-test. So if it is right tail t-test, it will be 1.96 plus, and if it is left tail t-test, then it will be minus 1.96. So as you can see that minus 0.60 minus 1.60, then minus 1.60 is coming around to be, I mean, greater than something called 1.96 or something like that. So that's why you have to compare with the respective tabulated t value, and then on that basis you will say that whether the statistic is significant or not. If you want to go for the proper statistic analysis, otherwise the p value will be sufficient. Just looking at the p value, you can say that p value, on the basis of p value, the statistic is significant or not. So it is up to you in whichever way you want to interpret it. So
Okay, sir.
crux of the argument is that the mentioned t stats are calculated t, not tabulated t.
Okay, sir.
Okay. Anything else? If no, then let me go to quickly to the next point of our discussion. So after seeing discussing the what you called the correlation simple and multiple part, then let us go to the diagnosis part. So broadly, I will be covering four part of it: multicollinearity, heteroscedasticity, autocorrelation, and model specification. And my focus will be broadly on model specification, because these part will be available in any forum or other, especially in textbook or maybe in YouTube links, etc. The final part, which needs to be understood, that whether there is an interaction term, whether there is a logarithmic transformation required, whether there is a need for a quadratic equation or a linear equation so far as the x is concerned, x1 square, x2 square kind of thing. So that's why let me quickly go through this part, then we'll be focusing morely on the final part, which is D4, model specification. So broadly, as I have told you, that the idea of collinearity is that if you have multiple what you call independent variable x2, x3, etc., then there is a possibility that the variables may be interrelated with each other. If there is an interrelation with each other, then there is a problem of collinearity. And because there is a possibility of multiple independent variables are related with each other, so that's why there is a possibility of multiple collinearity. So broadly, what happens if the nature is like the second independent variable and some coefficient time, third variable, they are added together, give rise to one, not any constant, specifically one, then accordingly there is a consideration of consequence of perfect collinearity, which is hardly the case. Otherwise, if it is give rise to some number, some other number, not necessarily one, some other number, and because of which you have added vi, then accordingly x2 and x2 plus 3 times xti or a times xti, it gives rise to 5, 7, 21.23 or minus 17.6, any constant number arises, then there is a concept of imperfect collinearity. That is the subject matter of perfect and imperfect. Sum them together for any linear combination. If equal to 1, then perfect collinear. If not exactly 1, any other constant, then it is imperfect collinear. Both of them are bad. uh, Perfect collinearity is a myth, or may arise, but majority of the problem, they revolve around the imperfect collinearity component. And that's why what happen if there arises a, collinearity of any such, whether it is perfect, imperfect, or anything, then the thing is that fortunately the blue property, that means base linear unbiased estimator property, is not violated. So in that context, multicollinearity problem is not that difficult to handle or understand or address. Even if there arises, no problem. I mean, if you leave it also, no problem. Anyway, whether we should leave or not, then that is a matter of discussion right now. But the thing is that the blue property is not violated. So accordingly, there is no need to be panic. Second thing is that, but still what happens, it may result in the T ratio of one or more coefficient tend to be statistically insignificant. That means some variable, because of the collinearity problem, some of the variables significant level is disturbed. And that is the problem for any researcher, because any researcher is always worried whatever may be the variable I have selected, that variable should come out to be significant, right? So if there is a problem with respect to collinearity, then T statistics may be biased, or T statistics may give you a distorted fact, right? And similarly, the third thing is that there is a possibility of very high R square value, whether it is R square or adjusted R square, it will give you very high R square value. So in that way, there are several what you call consequences of this collinearity or multicollinearity problem. How do you detect it? The detection problem will be several types. The first one is actually not mentioned over here, but I will give you a impression for that. Otherwise, it is simply VIF. VIF stands for variance inflating factor. So if you find out your variance inflating factor, and the variance inflating factor varies between the different combinations of the independent variable. So accordingly, if there are three independent variable x1, x2, x3, there is a possibility that x1 may be related with x2. Find out its VIF. If there is a possibility of x1 is related with x3, find out its VIF. There is a possibility of multicollinearity with respect to x2 and x3. Then find out its VIF. So there are three possibilities of VIF, provided that there are three independent variables. Higher will be the independent variable, higher will be the number of VIFs. And each of them you have to select whether there is a whether they are less than one, sorry, not one, there is a close to one, or they are very far away from one. Close to one VIF value will be in giving an indication that there is no multicollinearity problem. If the VIF value is found to be very high in nature, rule of thumb is 5. Some other texts they go for 10, but rule of thumb, according to my understanding, it should be 5 also. Even if it is less than 5, in some cases they consider to be multicollinearity problem, but broadly, if it is VIF less than 5, no problem. If VIF is more than 5, or further more than very high than 5, then definitely there is existence of multicollinearity problem. So that is the way in which you can detect it. And the alternative way is there is a tolerance level, and tolerance level is comprised of a reciprocal value of VIF. So definitely, if VIF is coming around to be 2, then tolerance level will be 1/2. If VIF value is coming around to be 5, then tolerance level will be coming around to be 1/5, and so on. So obviously, interpretation will be completely opposite for TOL. TOL will be as low as possible, will be bad for the researcher. TOL should be as VIF value will be very high, means 1 by VIF value will be very less. So accordingly, TOL value will be very less. So accordingly, that will be bad. So accordingly, just the opposite interpretation VIF. High VIF is bad, and less TOL is also bad. TOL should be as close to 1, that is good, and VIF is as close to 1, that is also good. high VIF will give rise to less TOL, and less VIF will give rise to high TOL. So in that way, these are the two broad things. And proceeding further with an example, so let us go to our regression analysis. Let us do the same exercise for this multiple regression, because there is a possibility of multicollinearity problem over here. So what we need to do before going to the VIF analysis, by the way, now the regression has its limitation. What happened in advanced mother or other advanced versions, or maybe in advanced add-ins in Excel, the VIF and other procedures will be just a matter of click. You will get the VIF thing. In other softwares also it is easy. But because we are doing it in Excel and we are not going for any extra add-ins, then accordingly we have to rely on the normal procedures which is known to us. So what happens, what we need to do, we have to go to data. So first thing is that let us go for a correlation coefficient. So till now we have done that. Let us select correlation. And what we need to do for correlation, we will not going to focus on the dependent variable right now. Rather, we will be depending on all the three independent variables. So income, wealth, and what you call interest rate, they are clubbed together under the input range, and the columns will be selected over here. And wherever you want to show the result of correlation, so what we need to do, you have to select the output range. And suppose I want to show my output over here somewhere in the S2. So S2 is selected. Now go to the back and press OK. And what happens over here, the correlation input image range contains non-numeric data. So okay, I think there is some problem over here. Okay. I'm sorry, I should not bring the labels over here, because okay, labels over here, I have not selected labels. So select the labels and then click OK. Now what happens, you will get the correlation coefficient table. Is it understood? Should I repeat once again the procedure of executing this, or is it fine?
Please repeat once
Yes, sir.
again.
Okay. So now what happens? There are three variables over here. All the three variables are in the column and rows respectively, and it is arranged in something called a triangular matrix framework. Right now it is a lower triangular, upper triangular is missed, because whatever is the correlation coefficient between income with income will always be 1. Similarly, wealth to wealth 1, interest to interest 1, because they are self for the same variable, it will always be 1. Now, what happens? There is an element of wealth and income. They are very highly correlated with each other. It seems to be 0.97. Whereas interest with income, they found to be 0.56. And with respect to interest and wealth, they are also found to be 0.53. So accordingly, interest and wealth, they are not that problematic. Interest with income, they are not problematic. But keeping income and wealth under one analysis, they may create problems. So this is just an what you call an elementary step to understand what is the possibility of problem. So problem hints that income has no problem with interest. I mean, we can club income and interest in our analysis, but not wealth. Maybe not wealth. I'm not sure exactly not wealth, but maybe not wealth. So what we need to do, so we have to find out the VIF score for that, because as I have told you, the VIF scores may not be available in the traditional models, the way in which we are doing it. So what we need to do, let us do the regression analysis, but one after another, by saying, let us do the regression where we will repeat the what you call the regression, but it is a simple regression analysis. And let us do the simple regression analysis 3 times, because there are 3 independent variables. So let us do the simple regression analysis for consumption and income only. So that's why I have selected Y as consumption, X only input, only income, not wealth and interest clubbed together. And labels selected, output range is there. I need not do residual assessment currently. And suppose where do I want to plot my result? And the results may be here. And let us go to OK. So I am getting this figure. Are you getting me? Is it okay till now?
Yes, sir.
Sir,
Okay.
can you repeat the steps of calculation of correlation between the income, wealth, and interest, sir?
Okay. So for correlation coefficient, go to data analysis, then go to correlation. Okay. Then within correlation, I have to select my input range. So I do not want to club my dependent variable consumption over here. I just need all the three independent variable x1, x2, and x3. So income, wealth, and interest. So I have clubbed them together. So it is C1 to E55. C, D, E, they are represented in terms of what you call the figures over here. And then if you okay it, you will get the result like this. Is it clear?
Yes, sir. Thank
Okay. So now what happened? We have to repeat the simple regression 3 times because there are 3 independent variables. So repeat the variables 3 times. So this is one part of the story. One part of the story indicates that this is the relationship between consumption with income. Second part of the story, go to data analysis. Second part of the story, for that, we need to find out, or in other words, what we need to do. Let us do one thing. Let us break this analysis altogether. Let us copy this information somewhere here and then paste over here. So income to consumption to income is over. The rest, what we need to do, copy the same thing and paste somewhere here. So what we need to do, consumption is my dependent variable, income is gone, so income is deleted right now, and interest is also not required. Suppose the interest also deleted. Next part of the story, income is done and wealth is done. So let me reduce income and wealth, delete it. Are you getting my point? So my point is that consumption and income is one-to-one simple regression. Second is consumption to wealth. Third is consumption to interest. I need to find out three simple regression result one after another. That is my objective, so that I can find out my VIF. So if that is the way, so go to data analysis, go to regression. So if you put a regression okay over here, so it asks me the input range. Now the inputs are here. This is the consumption, which is the input range. The output range will be similarly, the output range will be wealth now. And then output range is asking where do I show, where do I want to show my output? Suppose I want to show my output here. And then okay. So please remember, this is the simple regression analysis for which variable? Consumption and income. This is the simple regression analysis for consumption and wealth. Then accordingly, we have to find out the similar manner. Go to the simple regression analysis. So go to data analysis, go to regression, okay it. Then it is asking for the input range. Now the input range is consumption. Go to output range, and the output range is the interest rate. And then it will ask you where do you want to show my output. So for the output demonstration, let me select this particular portion, and I want to mention my output here and okay it. Is it okay till now?
Yes, sir.
Or is it
Yes, sir.
becoming too fast? Is it okay, right? So these are the three things. Yellow version is for consumption dependent, income independent. This is consumption dependent and wealth independent. And this is for consumption dependent and interest rate independent. So what we need to do, we have to find out the VIF. So wherever there is a R square value corresponding to that, what we need to do, because the formula of VIF, if you can see, the formula for VIF is this R square value, this R square value. Don't concentrate on these 2, 3. because 2, 3 is the combination of second and third variable. It may be any combination. So what we need to do, we have to 1 divided by 1 minus r square. So we know already what you call the r square value. So what we need to do, we have to find out 1 divided by 1 minus, within bracket, this is the r square value, bracket close, second bracket close, and click it. So this is what is your 0.003. This is, I think there is some problem. 1 minus 1, 1 by 1 minus r square. 1 by 1 minus r square. Anyway, this is
Sir,
not the right way.
sir,
Some problem
sir,
arises. Yes.
sir, the bracket segment is not good. 1 by bracket start with 1 minus, within the bracket 1
Okay.
minus.
So it will be 1 by 1 minus.
Bracket, no, bracket start 1 minus.
Okay, bracket start 1 minus
R
this
square.
series. This series. Is it okay? Let's see what
Yes.
happened. So it comes around to be 307.3296. This is what is your VIF. Can you see the VIF figure now? So this is with respect to consumption and consumption and income. So this is the consumption and income table of thing. Entire series is wrong actually. I'm sorry. I somehow missed it. Please don't do this exercise. The thing is that instead of going for consumption dependent variable, it should be income, wealth, income, interest, and wealth and interest. I'm sorry for that. I'm extremely sorry for that. This is not the ideal way. These three series need to be done once again by taking the 3 independent variables in nature. That means this combination will be income and wealth, which take any what you call variable as dependent, or any variable as independent, does not matter. So generate one simple regression for this pair, then generate second one with these 2 pair, then third one with this, then accordingly generate the r square and find out the VIF scores, not with the conjunction thing. I'm sorry for that. So what happens ultimately, you can get the VIF scores accordingly. By the way, this tedious exercise need not to be done, because in advanced versions of econometric softwares, it will be a matter of click, you will get the VIF scores for all the variables. So in that way, that will be easier for you. But if you want to go ahead with the MS Excel, then this is the way in which you have to do. You have to find out R square for 3 combinations, and then find out the formula, put the formula, and generate the VIF scores. And that VIF score will give you an idea that which 2 variable need not to be taken simultaneously. I'm sorry if I have, so what you called my way of explanation, troubled you. But finally, whatever I told you, is it understood to you, or should I repeat once again?
Yes, sir. It is understand.
Fine.
Understood, sir.
So,
Understood.
okay, fine. So next thing is that because there is a process with respect to, remedial measures are available. So what we need to do, so far as the remedial measures are concerned, that we have to apply. First thing is that do nothing and simply present the result as it is. Even if there is a multicollinearity problem, the recommendation suggests that don't do anything. Second thing is that if you have a model containing several variables and legitimately belong to the model, it is better to leave them in the model, because as the model is taking from some economic theory or some logic, and accordingly those logics suggest that even if they are found to be insignificant, but they should be kept in the model, then please keep in the model. Otherwise, there will be a problem arises in other types. Third thing is that, but if you have some data fishing or data mining things that you want to do, then that data fishing, that mining thing can be easily taken care of with the help of a stepwise regression. I'm not going into the detailed part of the regression part over here. What I'm trying to show is that, Suppose we have 7 independent variables over here, and we do not know that which one should be kept in the model and should not be kept in the model. Then what we need to do, like the way in which we are doing right now, you have to go ahead with a simple regression model with y and x1 independently, y with x2 independently, y with x3 independently, and find out which particular variable t statistic is found to be significant as well as greater. Then accordingly, out of all the 7 variables, x5 variable should be there in the basket of selection of variable. So accordingly, x5 should be there in the first category. Second category thing, once you will understand that out of 7, x5 is important. Additionally, with x5, which one further is important? So accordingly, x5 will be one independent variable. Along with x5, take x1 as the second independent variable and y as the dependent variable. Find out t statistic. Additionally, with x5, add x2. The addition does not means x5 variable will be added with x2 variable. No, x5 variable is the initial variable. Along with the x5 variable, take the x2 variable and accordingly generate the second step regression analysis. And in the second step regression analysis, follow the same pattern. Whichever is the significant one and whichever is the highest one, consider that variable to be the second most important variable which should be kept in the basket. So accordingly, in the first round, we have already put x5, fifth variable. In the second round of stepwise analysis, we have found out that along with x5, we need x2. And similarly, do the exercise continuously, and ultimately you come out with a solution that further, once you obtain x5, x2, and x4 in the third round, up to the completion of the third round, in the fourth round, what we can see that none of the further variable, they are found to be significant, and accordingly there is no need to take more than x5, x2, and x3. Sorry, over and above x5, x2, and x4. No need to take x1 and other variables. And on that basis, by taking those 3 variables, you can do your analysis in a more simplest and a better manner rather than clubbing for all the 7 variables. Is this analysis okay?
Sir,
Have you
here I
understood
have,
this?
yes, sir, yes, sir. I
Ah,
understand. Sir, here I have one doubt that, sir, in
okay.
stepwise regression, there are two other models that forward selection, backward elimination, sir. Sir, what
Okay.
is the difference between these two models, sir? Forward selection
Which one?
and forward selection and backward elimination in stepwise regression, sir.
No, that's what I'm saying over here. I mean, once you have selected the one x5 over here, so once x5 it is done, then it is a forward selection mechanism.
Okay, sir.
Backward thing is that you keep all the 7, then gradually go for the just the reverse way. I mean, logic. That means you drop one, then see what happens. Then whichever is the drop one, then find out the two drop one and so on. So instead of going for dropping the things, that will be creating problem for us. So it will be always going for a forward movement kind of thing. That is my understanding. That's why I have kept for the forwarding mechanism, not for the backward. For the backward mechanism, we need to take care of other type of procedures also, like what is the initial adjusted R square value, whether the adjusted R square value after dropping any 1 or 2 variable significantly increase or not, because if it is not increasing, then accordingly those variables they might have put any impact on our analysis, but I have deliberately kept them out. So in that way that will be creating problem. So for me,
Okay,
this forward movement stepwise regression will be a better approach instead of going for a backward movement.
okay, clear, my guides. Thank
Okay,
you, sir.
fine. So this is the one way of handling the multicollinearity problem. Otherwise, if there is a multicollinearity problem, ask for if you have selected your model according to the theory and the theory suggests that keep the variable along with it, then don't leave any 7 variable out of it, because you know that all the 7 variables are in accordance with the theoretical logic, and that's why we will not leave it. And that's why even if there is a multicollinearity problem, present it as it is. No need to be worried whether if you keep 7, then only 3 comes to be significant. But if you go for this type of 3, then all the 3 variables come to be significant. that will be always there. So that does not mean that whatever will be the theoretical justification for 7 inclusion, because you are getting insignificant, you will just drop them as per our whims and wishes. That should not be the ideal way. That's why the first solution is, even if multi-quality problem arises, leave it. Otherwise, if you are okay for data fishing, data mining kind of thing, then go for it. Otherwise, there is a procedure of principal component analysis also. Clubbing 3-4 variable, they may give rise to a particular index, and accordingly that particular thing may be useful for it. But because of not sufficient time, I'm not going into that part of the story right now. So now there is a problem with, there is second problem with respect to heteroscedasticity. If there is a heteroscedasticity problem arises, then there is a possibility of
Excuse me, sir.
presence of outlier.
Excuse
Outlier
me, sir.
because of outlier. Yes.
Sir, sorry for interruption. In multicollinearity problem, if we take the data of time series manner, and if you take the previous 1 year lag period, then the data of current year is collinear to the same data in the previous year. Then in this case, the collinearity might be very high. Then how could we solve such kind of problem in time series data?
You see, in the time series data, unless until the nature of analysis required for the dynamic, modeling, the dependent variable lag periods should not be taken into consideration as a right-hand side variable. And if it is a dynamic dynamic regression analysis, then it has a different way of mechanism. Only adding one dependent lag dependent variable will not be the usual econometric exercise anymore. So if you want to add them, then it has its own way of analyzing and handling the analysis, because for that we have to apply for the dynamic regression. And in the dynamic regression, when we include the dependent lag dependent variable, then in that case it needs justifications also, whether there is a what you call a noise effect arises or not. If there is a existence of noise effect, then you keep it. Otherwise, there is no necessity of it. And this simple regression or this type of normal regression that we're doing, they will not be appropriate regression further. For that, we need to adopt a different family of regression analysis. That's why I'm said in the beginning that this regression analysis is not for universal cases. It depends on the nature of the variable, whether they are ordinal, whether there is numeric, whether there is categorical in nature. Accordingly, those regression analysis, they have different types, and same is also the case for the dynamic regression. I hope I have tried my best to give you a satisfactory answer.
Yes, sir. Yes, sir. Thank you,
Just
sir,
by
for the
avoiding it.
response.
Okay. Okay. Thank you. So now moving to the heteroscedasticity part. The heteroscedasticity part arises only when the error term, if you arrange them, find out its variance, the variance is found to be constant or not constant. That means whether for each time period it is changing, or whether it is for each cross section it is changing, then accordingly there is a problem of heteroscedasticity. If you come across with such heteroscedasticity, then it may be because of certain outliers in the data, then trace it and removal of it. Second, if there is a possibility of incorrect functional framework, that means a particular variable needs to be log transformed, or maybe exponentially transformed, or maybe an interaction term need to be there. So accordingly, if you have not addressed them, because of that, heteroscedasticity problem may arise. Third thing is that the transformation is incorrect one. That means for one thing, there is no need for any log transform, but we have done it. Then that also may lead to heteroscedasticity problem, because it is always a fascinating case. That is a matter of discussion for me, so that I will tell you shortly that majority of times the researchers, they do they do one thing, whatever may be the nature of variable, go for a log transformation. And once they go for a log transformation, then they use the normal regression technique, and then they will say that we have normalized the data, blah blah blah, and accordingly our problem is solved. But that is not the actual case. If there are certain data for which log transformation should not happen, and if you have done it, then you have already done a problem. So heteroscedasticity problem may be because of this type of transformation, which need not to be transformed, and we have transformed on our own logic or on our own understanding. So that is also a problematic thing. So these are the problems, or these are the possible way of heterostricity problem. And now, so far as consequence is concerned, it is dangerous. It is not that what you call uh, investigator friendly. If a multi-clonality problem arises, the investigator may not be panicked. But if there is a heterostrategy problem, it will what you call affect the best component of the blue property. So it will be no longer blue; it will be only lu. So best component will be missed out of it. So accordingly, it will be affecting the coefficients in terms of consistency, in terms of biasness, in terms of other characteristics. So the thing is that we can go for any kind of weighted least square method to address this type of thing. Now, before going to the weighted thing, these are the way in which we can trace the heterostricity. So what we need to do, that there are several ways of doing it. Again, with Excel, they will be very difficult to demonstrate it. Not very difficult. I mean, we can do it because I have given you the framework for that. One of the most prominent way is that there is a Bruce-Pagan Lagrangian multiplier test, LM test. So what we need to do is just simply go for a multiple regression like the first one, then predict the residual, the way in which you just click a mouse, the residual series will come. Then what we need to do, whatever the residual series arises, then go for its square term. So whatever the residual series will come, just square it up. And once you get the square term, that square residual term should be considered as a dependent variable, and all other independent variables should be in the right hand side. So accordingly, you keep the right hand side variable as it is in the initial case, but instead of the y dependent variable, use the residual square term and go for it. Then what happened? It will give you something called, it will give you something, the Lagrangian multiplier statistics. And the Lagrangian multiplier statistics will be generated with respect to the R square value, because as we know, doing any regression, it will give you an R square figure. Then that R square figure, if you multiply it with the number of observation, then that will give you the Lagrangian multiplier method, Lagrangian multiplier coefficient. And then that Lagrangian multiplier coefficient or statistics, if it is found to be what you call statistically significant, then accordingly there will be a presence of heterostricity problem. Otherwise, there is not. So this is the one way. Similarly, there is something called Glacier LM test, where instead of going for square term, you find out the modulus value of it and do the regression. Or there may be something called Harvey-Godfrey test, where instead of going for only square term as the variable over here, go for a logarithmic transformation of the square error term. Or there is something called Park test, there is something called White test. More or less, this approach will be similar, but only a matter of degree arises, varies, but somehow the heterostricity problem can be traced easily. Only thing is that the residual error term, square term will be dependent variable, and all other right hand side variable as the right hand side variable, and do a regression, find out its R square, multiply with the observation, n into observation will give you LM statistics, and this LM statistics, they follow a chi-square distribution basically. And you find out the chi-square distribution for something called 0.95 as the base, 95% level of significance, and degrees of freedom is k minus 1. So if you have three independent variable, then 2 degrees of freedom, and go for 95% confidence interval, sorry, 5% level of significance tabulated value. Or if you have 10 independent variable, then 9 degrees of freedom with 5% level of significance chi-square value. That chi-square value will be your tabulated chi-square, and whatever is n into R square, which is LM statistics, that will be considered as a critical value. So if a critical value is greater than tabulated, then reject null hypothesis. Reject null hypothesis indicate that there is no heterostricity, or accordingly there is a homoscedastic case. So in that way, you can check the heterostricity solutions. And example, I'm not going to repeat now. Remedial measure is that there are different versions of modified OLS called GLS and WLS over here. And in this way, you can address something called the heterogeneity problem. Now, in the third line, the autocorrelation problem, as I have told you, the error term will be related with the previous values of error term. So what happens over here in case of the autocorrelation? The way in which it is affecting the blue property, now it is going to affect the efficiency parameter of the blue property of OLS, and autocorrelation is also problematic problematic situation. So we have to address the autocorrelation problem like the heterogeneity problem. So heterogeneity and autocorrelation problem can be very simply what you call sorted out with the help of advanced econometrics by the help of something called robust command. I mean, in Stata or in some other version, if you go for a robust standard error component kind of thing, that can be addressing autocorrelation and heterogeneity problem. But anyway, with Excel will be difficult, so I'm not going to that part. Detection part will be like the way in which graphical method or maybe something called Darwin-Watson D statistics. So as we can see that there will be a process like this. So whatever is the error term and the error term, they will be differenced with each other, get the square term and sum it together and divided by the sum total of error term. So that will give rise to D value. The D value has a range. It will be varying from 0 to 4. Close to 2 value, the Darwin-Watson test indicate that there will be no autocorrelation or very marginal autocorrelation. Equal to 2, no autocorrelation. If it is moving away from 2, close to 0 or close to 4, then there is a element of positive or negative autocorrelations accordingly. So in that way, there is a formal way of detecting autocorrelation. In addition to DW statistics, there is something called Brius-Godfrey Allen test also there. There is something called Darwin's S test also there. So these tests will be not possible to cover because I need to focus at least for 10 minutes. I'm sorry, I'm extending my lecture right now, but that 10 minutes discussion will be very important so far as my personal understanding of regression is concerned. So let us go to that, which is the model specification error. Now, in the model specification error, there are several versions of it. Maybe some variable which need not to be incorporated, already taken in our analysis, may lead to over specification problem. Some variable which already they are in the model, but they should not be taken into consideration. So that give rise to under specification problem. And the final one, which is functional form thing, in that context, I want to draw your attention. Now, what happens over here? Many things, sometimes what happen, the non-linearity component play a very important role. So what happen? The students, they come out with certain variable. So right now there are 4 variables over here. What they took, they go for x1 as the normal one, normally linear. They go for x2 as a quadratic form. They go for x3 as a normal, but they finally do one thing. They multiply x3 with another variable called x4, and there is an interaction term. So now nonlinearity arises either because of quadratic form nature, or there may be a nature of interaction term, or there may be a nature of logarithmic transformation or something like that. Now, what happens? The problem is that the way in which we have interpreted previously, that means if x1 only changes, then beta 1 times change happen to the y dependent variable. But same is not the story for other variable, because x2 is present 2 times in the model. So accordingly, the marginal or the partial effect analysis says that even if you find out the beta 2 as the coefficient, that does not mean that when x2 changes, beta 2 times effect will be the effect on the dependent variable, because it is also depending on several other things. So in that way, the clubbing of several variable will make the analysis troublesome. So this is the case with respect to the quadratic form nature of the x2 variable. This is the nature of the variable because of the interaction term and so on. So what happens broadly? So when there is a regression with a quadratic term, so at that time, the nature indicates that if you put the quadratic term, And if you do not put the quadratic term, then what happens the analysis? Either it may happen that without the second square term, then in that case, this is the partial analysis or the marginal effect. Higher is education, more will be wage, and the interpretation will be 0.51 kind of thing. But when we add for the square term, it is not like that. It is minus 0.607 is the effect of education on the wage. Rather, we have to do one analysis. That means we have to go for this type of analysis. That means minus 0.607 will be the case for taking normal education, and because there is a education square term over here, so that education square term will be multiplied with 2 because it is a quadratic form. If it is cubic form, then there will be further complexity in the interpretation part. Because it is a quadratic form, so we have to find out 2 times the coefficient of the square term, like 0.0491 over here, and then you have to multiply with the education value, because the interpretation is like this. It is beta 1 plus 2 times beta 2 x1. So beta 1 value will be obtained from this minus 0.067. Beta 2 value will be obtained from this it is like 0.0491. And ultimately, when you log with 2, if you multiply with the 2, then we have to multiply some number for that. And those numbers, they will be the education value or the mean values of the education. If you go for the mean value, and suppose the education series is known to us, and if you find out the education mean value comes to be 12.6, then 12.6 if you multiply, then the figure comes around to be 0.63. This 0.63 is actually the ultimate effect of what you call the education on the wage variable. Normally the students, they don't go for this type of interpretation. Remember, this 0.63 is nowhere in the picture so far as the normal coefficients are there. The normal coefficients are either 0.067 or 0.0491, but these figures will be of no use unless until we go to this level of analysis and say that ultimately, if education increases or decreases by 1 unit, then it will affect the wage rate by 0.063 unit, 0.63 unit. And this is the number which is generated by following this type of process, which is known as the marginal effect analysis. And broadly, the students, they misread it and interpret it as a very technical manner by interpreting those two figures. And those two figures interpretation will be of no use. Practically speaking, they will add no value to your analysis. So be what you call cautious while interpreting the quadratic type of equations. And same is also case for another quadratic form where it is inverted usage. This is the case where I have shown it for a what you call the normal usage curve, like average cost or marginal cost kind of thing. Whereas over here, this type of analysis will be what you call something like production value, total product or something like that. So in that case, wherever there is a quadratic form, interpretation play a very important role. It has to follow a particular pattern, not the normal procedure of interpretation. Then coming to an interaction term, whenever there is an interaction term, for example, the first model, as you can see, there are 3 independent variables are mentioned. The 3 independent variables partially, marginally, they are found to be positive and significant. That means education positively affect, experience positively affect, tenure positively affect independently to each other. But when you go for the interaction term, as you can see in the model 2, the interaction term is between education and experience. What happens when you go for the interaction term? Neither the interaction term is found to be significant, nor even the experience term, which was previously found to be significant, now loses its significance. So that does not necessarily mean that interaction term is important or non-important. It will give you an impression that education only affects your waistlet, but experience, when it is interacted with education, they are not going to affect your wage level. So that's why interaction term interpretation is also very important. Otherwise, people, they mechanically interpret that education was previously the positively significant, now also positively significant, but experience loses its significance level, and interaction term is also not found to be significant. But that does not make any sense. Interaction term is important, and wherever it is found to be significant, there only you have to interpret it. Like over here, as you can see, when you go for the, instead of going for education and experience interaction term, when you go for experience with tenure, then it is found to be not only independent, individually significant, but also jointly significant. But here also there is another point of problem. Individually, they are positively significant, as in the normal case, first case, but the interaction term is found to be negative. That means what? That experience independently positively affect which, tenure independently positively affect which, but when they jointly affect, joint effect is found to be negative, indicate that they are actually contributing to each other inversely. That means experience and tenure, they are actually clashing with
Sir,
each other. Yes.
What is the third column actually shows? It is the same, I think.
Is it the same?
No, it is not
Is it
same.
visible to, is it
Yes, it is
visible to
visible.
you?
Yes.
Yes.
What is the difference in
So
between
the
the second and
third model indicates that it is including experience and tenure as the interaction term. Second model indicates that it is the education with experience. Education and experience interaction term is not repeated in the in the third model, and experience and tenure is not repeated in the second model. So in that way, second and third, they are different to each other. Can you see the interaction term? The model
yes,
2 takes interaction term, but the interaction is between your the first and second variable. Whereas model 3 is taking the interaction term, where it is taking the interaction between second and third variable. In that way,
yes,
the
sir. Yes,
model 2 is different from model 3.
I got it, sir. Thank you, sir.
So in that way, what I'm trying to say is that whenever they are independent, individually taken like this, they are also repeatedly finding the similar pattern. But what happens when they are combinedly taken? The combined effect is significant and negative. That means independently, individually, they are positively affecting wave rate. But when they are taken jointly, they are actually, pushing back to each other. That means experience is pushing to tenure, and tenure is pushing to experience when they're clubbed together. So whenever there is an interaction term, its interpretation is also very difficult. I mean, not that much easy. I'm not saying very difficult. It is not that much straightforward in nature as we have taken into considerations normally when there is no interaction term. And in the similar manner, the effect of marginal effect can be analyzed. Finally, when there is a rescaling variable, that means rescaling tells means what? Suppose there is a salary which is a dependent variable, and sales is a independent variable, and profit. Salary is a function of sales and profit. Now, what happens if the salary is already in thousands and sales is in $1 million, or sales is in thousand and salary is normal dollar? Then accordingly, they have different type of effect in the coefficients. As you can see that if you go for rescaling your dependent variable only dependent variable rescaling, then it is going to affect the coefficients in in a specific manner. The interpretation is mentioned over here. If you can pay attention, if a dependent variable is multiplied by 1000, that means when you convert your salary, which is already in thousand, to normal one, when it is not in thousand, in the normal dollar form, then the coefficients are multiplied by 1000. Whatever is the coefficient is 0.0175. If you multiply 1000, it is coming around to be 17.49. So accordingly, if you rescaling your dependent variable, then that is the typical manner in which all the coefficients are actually multiplied by 1000. Whereas if you go for the rescaling of your independent variable, like if you go rescaling your independent variable by 1000, that means if you convert from sales to what you call normal thousand type of category, then what we can see, the coefficient is actually divided by 1000. Here, the comparison from 0175 to 17.49 is 1000 is multiplied, because the dependent variable is rescaled by multiplying 1000 in the dependent variable. Whereas if you go for the similar type of rescaling in the independent variable, the similar type of independent variable, as you can see, that they are actually divided by 1000. 17.49 divided by 1000 will be something like this. 0.0175 divided by 10,000 1000 will be something like this. So in other words, what I'm trying to suggest is that Rescaling a variable is a very important thing, and you have to be very careful where you have to go for the rescaling. Whether one variable is $1 million, another variable is $1 billion, even if dollar. I'm not going for dollar to rupee conversion cases. Again, it has its own challenges. But even if it is converting from million to billion or something like that, you have to be very careful so far as the rescaling is concerned. And ultimately, finally, I'm sorry to extend the argument. Ultimately, the final point is with respect to my favorite point so far as the logarithmic transformation is concerned. Try to pay attention to this final point, that logarithmic transformation is not the usual practice that we generally do. It should not be done. It should be actually done with a very, very careful observation. Because sometimes the variable like y or x, they are expressed as logs or log y or log x. With logs, the coefficient interpretation is in percentage and elasticity. So the way in which we interpret previously, the marginal analysis is no longer marginal analysis, rather it is gone to the elasticity analysis. If your objective is asking for the elasticity analysis, then do it. Otherwise, if it is asking for marginal analysis, then you have to convert the elasticity analysis to marginal analysis. Then you have to interpret your answer. But again, that is a drawback with respect to the empirical researcher. They hardly pay attention to that. They go for logarithmic transformation, go for the elasticity component, and now they say that if there is a 1% increase, there is a this percentage increase or decrease in the dependent. But if I am not interested for a percentage increase, if suppose I want to know that if independent variable increases by 1 unit, what will be the effect on the dependent variable, then that percentage interpretation informations will be no longer relevant for me. Then how to do that? Again, it has its own way of narrating the story. Next point is that variables such as age and education, which is measured in terms of years, they should not be lagged, because there is no point in converting 54 years or 74 years or 34 years to logarithmic transformations. It will always be in terms of a particular thing which will be of no value. Same is also the case when the already variables in percentage. Whenever there is interest rate or something like that, converting the interest rate or maybe something called the performance label, or suppose a index is measured, converting the index to logarithmic transformation, again also no use. So in that way, the logarithmic transformations that we generally do, we should be very careful while doing it, because the linear form, the log linear form, there is something called linear log form, and there is something called log log form. Log log means both side log. Linear log means the dependent linear, the right hand side log. Log linear means the dependent log and the right hand side linear, and linear means both of them linear. So which one is the best one? It depends on something called the R square and something else like AKK information criterion, Squartz criterion. There are several model specification criterion are there. On that basis, we can come to know that which model specification should be adopted, why and how. If you do not understand that spirit, then whatever may be your answer and interpret it mechanically, that will be a futile exercise. Thank you very much. I end my discussion over here. If you have any observation or query, then you are most welcome. And I'm sorry for extending my lecture to almost 17 minutes more. Thank you, sir. Thank you very much.
Yeah, thank you, Vikas. I think you are continuously speaking more than 3 hours, 20 minutes. I think now it is 2:20. So if yes, before I say something, if you have any questions, I understand. I think I should stop the recording fast.